All right. Hello, everyone. Welcome. How are we all doing? That was so close to being smooth, but I just messed it up. All right. Welcome, everybody. How are we doing? Awesome. Phone here with the chat. Welcome, RH Pid. How you doing? Welcome to the stream. So, what are we working on today? So, I think we'll give a brief recap of last stream, and then we'll make a start. So as you can tell by the title, we're still working on the renderer from last stream. Last stream we got not that one. We got a window. We got an X11 window working. We got some very terrible input stuff, and we initialized a Vulkan instance and a Vulkan device. Hey there, Glorious. How you doing? Welcome. Good to see you. So what we're trying to do is get some minimal part of the code work, like visually doing something, so we don't overcomplicate it. So we're just getting the bare necessities, the most minimum set of features to sort of get things working, and we build around that and try and keep it working as much as possible. Yeah. So last stream we actually started from nothing, and oh, Glorious, welcome. Thank you so much for that sub. Really appreciate it, and welcome. Welcome to the club. You get all these beautiful emojis. I've just added a new one actually. We added Reggie. We added some Reggie. So you got some Reggie sad and Reggie thinking as well. And also you can get access to the code base if you check out the Discord channel. Link it up and you can get this code in your system and have a bit of a play. Hey Mad Flash, hey Phoenix Firewings, welcome guys. Good to see you both. So we started from nothing and we made basically everything in this repo last stream. So we've got a scripts folder where we can basically this is our build system right now, a very simple build script where we essentially just make the build directory, we run HCC, which is our custom shader compiler, and then we run Clang to build the actual game using a single compilation unit. And then we have a third-party folder where we stick our dependencies in here. So we've got bstack trace for stack traces. So anytime there's an assertion or anything, you see a stack trace. Super nice. And a HCC goes in here as well, so we just have it bundled in with the repo. And then in the source folder, we've got a main file where the main function is, a core files where it's basically like memory utilities, memory allocators, collections, and stuff like this. But we haven't basically got any of that in there. It's very minimal right now. It's literally just got a couple of memory utilities in there right now. It's super minimal. We've got an operating system folder where we have our OS abstraction. So any OS specific code goes into these files. So OS Linux, OS Windows, for instance. And then there's an interface that gets implemented, which for now is just an event. And then opening a window and getting the next event. So it's very minimal, as we've been saying. We're just in the bare necessities. We've got GPU abstraction, which is sitting on top of Vulkan. Again, it's very minimal. And this is our like graphics API. So a bit like, this is our OpenGL, right? Our own OpenGL, essentially, but not obviously OpenGL. And then we have our graphics part, which is actually the game using our own graphics library. And yeah, we also have our shaders in here and everything like this. So I'll bring up the editor and we'll zoom in a little bit on that GPU side of things, and we'll get into implementing the Vulkan stuff. What are we making? A game without an engine, Mad Flash, sir. We're so we're currently working on. So I think I should give like a high level overview of like what we want to do for the next so many streams. So we're probably we've got this window, right? It's a pretty nice window. It's black, you know, it's not white and blinding everyone's eyes, so it's very nice, fits in with the dark theme. But we want to try and clear the screen with a different color, with compute shaders only. So we're going to get the compute shader working and clearing the screen. So for that, we need to do all the Vulkan backend code to get our GPU API up and running. And then we're going to render a little box on the screen. And that box will be our player. And from there, we're going to try and program up some keyboard input, get the box to move around. Also, get like a gamepad. So try and get this like PS5 controller maybe hooked up, get that working, moving the person around, moving the box around. And then probably get some debug UI so we can like change the size of the box or something like this and just have some debug widgets. And then from there, we've got all the stuff we need to do some development in the 3D for the 3D graphics, because we want to actually do a 3D game using compute shaders only. So we're gonna be from there doing some research and development with the debug UI and just writing compute shaders and just having a play. No, not even SDL. No, not even SDL. From nothing but the OS and a few single headers. I know it's a shader compiler, but could you make it possible to also compile to OBJ through indirect Clang or GCC classes? So yeah, like the thing is, I haven't fully implemented like the whole of the C language. I've got pretty close. I think we're still gonna get pointers to work. But theoretically, I could write a backend that just writes straight out to like x86 and does it very terribly, right? Yeah, but the issue is, it's just I don't really want to work on it right now. I want to like work on a game. Like I've spent like a year and three months working on that compiler, so it is going to go on the back seat for a while. I'm still going to work on it off stream, but on and just do small little fixes. But I'm mainly trying to figure out what's wrong with it by using it. So that's the plan from now for the current time. Thank you, sir. Appreciate it. Probably get a haircut soon. It's only a bit too long, but thank you. Personally, I would like to build my program with one compiler instead of having to faff about making a build system to handle two compilers. Sure, I don't know if that's too much of a big problem, really, to be honest. Like, it wasn't rocket science. Like, there's many more hard problems. Like especially when you do Vulkan, that is way more harder than just getting a command to fire in a build system, right? Awesome, Glorious. So sorry I didn't see your thing there. Thank you. Yeah, cheers. Thank you for the support. Appreciate it. I have a question. Can you give me an idea for a 2D game that I could make? Not really. I have no idea. Make something personal for you. Do you find any disadvantages or advantages of doing game dev with Linux distros? Um, so the thing I like about Linux is the fact that, like, with Windows, it's very there's just so many things which just like, annoy me about Windows. For Linux, there's less things that annoy me, so it's maybe more of a personal thing. But like Windows is quite slow in some areas, like compared to Linux, and um, yeah, that's like, and I just like the experience in Linux. Like, it's just typically seems to be a little more zippy, more responsive. Um, Obviously, if you're coming from Windows and been developing Windows for a long time, it might not be your sort of thing. But I've been using. I learned programming in Linux from the get go since I was like 15. So, like, yeah. Um, like I personally find it more developer friendly, but people who use Windows will find Windows more developer friendly. So it's more like it's a personal thing. Like try out Linux and see what you like about it, and just yeah. Oh no, yeah. Like if you want to, the problem is like if you want to support Windows, like when you're doing game dev from Linux, like you obviously need to have a Windows machine and switch over to test it on Windows when you get to that point. And it'll be a bit of a pain when you release something, I imagine, because if you develop on Linux, you have to make sure, all right, I've got enough to release something now. Should I? I've now got to switch over to my Windows machine and test it. And it's that to and from you've got to do, right? Hey, Don. Why don't you use Uni? Because Game Engine's done. Don, we need your Game Engine video. We need it. It's so good. I was speaking to Perry about that Game Engine video a few months back, and we miss it. We miss it. So the way you do those high kicks, it's impressive. It's impressive. Why can't I just use LLVM as a backend? Yeah, it could, but it'd be effort. It would be effort to work on. Yeah, man. Oh, just about to get right into that. Hey, Nico, how are we doing? It still plays. Have you got a link to that video? It's awesome. I thought you took it off your channel. So what we have is we have this gfx dot h. This is our like graphics rendering thing. So in like the main loop, we'll call like render frame, right? And then in here, this would be our like, oh my days. Yeah. You know, maybe. All right, I was a bit confused because I think I started off with the wrong one. GPU. Right. So this is our graphics API right now. I'm probably going to change it today since we started working on it. But essentially, we just start recording a command buffer. We end recording the command buffer. And while we're recording the command buffer, we can do some dispatches. We can dispatch some shaders. And then after we've recorded our command buffer, we can just simply submit it to the GPU and off you go. So it's very minimal right now. Obviously, we need to add like support for resources and stuff like this. But we've got a hard-coded one, which will be the texture, which would be the the back buffer or the display, and we'll render to that. So that's what we're going to start off with. So right now we simply start recording the command buffer where you put dispatch in there. We upload our constants to the shader, and we do it for the size of the screen. And here's our shader, right? So our shaders are declared in a C file here. There's only got one right now. And it's designed to clear the screen. So last stream, I went all in and explained what dispatch index is. how it basically gives you how in this context it's basically giving us the texture coordinate, because the way we'd maybe I should go and explain this again. Hey Persa, how you doing? I still got the video. Legendary. Harry still got the video. Yes. Yes. So good. So good. That's the one I was looking for. Right. Bookmark. Right. Thank you, Don. Appreciate it, sir. And also, if you guys don't know that man, Don Ho, he streams. You should go check him out. Does some more C programming as well. 69 subscribers, very nice. Exactly, 69. Wait. Oh, it's 36. Hey, not so red. How you doing? Doing good, man. Doing good. Hope you're doing good. So essentially, like in a compute shader, you essentially have a local group size, which is 8 by 8 threads. So 64 threads in this local group. Now, when you dispatch it, right, you launch how many groups. You're saying how many groups am I launching of threads? So we have to divide it by 8, which is the local group size, and we have to round it up when we divide it. And then so then, like in the shader, what dispatch index is essentially that the group index times by the local group size plus the local dispatch index. Like if we see, we see this here. So we've got local dispatch local index, which is a local offset from 0 to the local group size, right? And you got the group index, which is essentially from 0 to whatever the dispatch dimensions were. So as in the number of groups that you're launching, right? And then dispatch index is the combination of these, where it's group times by the size of the local group size plus the local index. So if we were to just take a step back and see what we're actually doing here, what we're doing is, here we go. What we're doing is we are simply clearing the screen, and the screen is 800 by 600, and we're launching that many groups to clear an 800 by 600 screen. But because we're rounded up, we could essentially, if this is not directly divisible by 8, you can have some threads that go off the texture, and then you'll be accessing out of bounds. So I described all of this last stream, that this coordinate could essentially be out of bounds. And then I didn't go and actually fix the problem. So we're going to do that now. So what I want to say is, like, if any of these which we're probably greater than so if the coordinate is greater than the output dimensions, this is probably not going to compile too well. I've got to check to see the bugs, but yeah, that should be fine. Yeah, then we return. So if the coordinate is out of bounds, greater than or equal to, right? Then simply do not try and store anything in the texture because you're going out of bounds. Right, we need to do that then. So let's see if that compiles. They're saying any G is not declared because any G is part of the mask library. Let's bring that guy in. Hmaths. Oh, no. I need generic. Generics, because I use C generics. C11 generics. Right, now this one's complaining. Oh, my greater than or equal to F16 is a wrong. I don't have one of those. Huh. Let's go to here and see what's up. Hang on a minute. Third party HCC, Hmaths, libhmaths, generics. Oh, you got to include it yourself. Okay. Don't mind me. Not know my own maths library. Scalar, vector, matrix, I guess. Let's get it all in there. There we go, much better. So that can pass now. Good. So if we go back to yeah, so if we go back to this, like our main render frame function, I guess called every frame. All of this code that is being called is not actually implemented yet. So we're going to go ahead and continue to implement this. So if we hop into, so all of this is basically not implemented. So we're going to go into GPU Vulkan, and we've got this sort of back-end initialized. So we're going to continue on this today. What kind of game am I making? We're going to be doing some R&D first. So we're going to try and find we're going to be using computer shaders only. And we're going to try and find an art style first. And then after we've found an art style, we're going to then use that as part of the... we're going to find out our pros and cons from going this direction. And then sort of using that as part of the thing to help us decide on what we actually want to make, basically. But yeah. Along with many other things as well. Hey Day, do you want FAQ on screen like Togglerbit does to answer similar questions? Probably a good idea. It's probably a good idea. Maybe I can put it as an over. Yeah. I'll think about that. What did it get done? We got a window open, Perry, and we're just about to. We started doing some VVVVV without you, but we're carrying on with that now. So we've created an instance, a Vulkan instance with its extensions, and we have created We've selected the physical device in a very poor way. We've got a compute queue, and we've created the physical device. Sorry, we've created the logical device. So now we're carrying on from here. So what things do we need? Rust. You got around my thing, Don. Say Rust the real way. There's no Linux Wayland. No. No Linux Wayland in any way. Okay. So what things do we need to create in Vulkan in order to get things on the screen, right? So we need our VK descriptor set and whatever. So I'm just going to say descriptor star for all the other things in there. This one's very easy to do because HCC helps us do this. We'll see that in a bit. We need a swap chain. The swap chain is basically or KHR, because it's technically a Chronos extension, but whatever. This is our thing that we will ask, that will create our VK images for. It will talk with the display manager, display server. They'll basically create our images. And we can use those images to render to. So this is. We'll get one each frame, and then we'll call this each frame here. And it will return that swap chain image for us. So we need that thing. We need a command buffer, a command pool, which creates command buffers, and we need we submit those down queues, right? Then we need a timeline semaphore, and we need probably a binary semaphore as well. So I've not done timeline semaphores yet, but it's my first time doing them. But we'll explain those when we get to them. So these are the things we basically need. So I think let's just start. Yeah, we need to create everything. All the things. So let's start with the descriptors. Talking about descriptors, descriptor sets, and what is a descriptor? What's a descriptor set? What's a descriptor set pool? And we'll probably it's quite a big one really. But let's see if we can explain it simply. So in a shader, if you were to if you're familiar with GLSL or HLSL, what you actually have in shaders is this global variable thing. And they have maybe texture 2Ds of something. And they have typically you say U texture for uniform or whatever. And it has some binding on it. I think GLSL likes to have this binding, and you sort of reference the binding from the CPU side to sort of set the descriptor. And this thing here is a descriptor, right? The thing that's actually from the shader side, when you actually use this texture and read it, you're reading the texture descriptor. So what is a descriptor exactly? Well, it's effectively it's metadata for the texture. So it has a pointer to where it is in memory, where the actual texture data is in memory. What texture is it? Is it a texture 2D? Has it got it's got tons of information about what this texture actually is. So when you actually try and sample from it, it can read the metadata and actually act on that. And it varies across platforms. So the reason why I can't list them is because they kind of keep it hidden. But I think if you were to look at AMD RDNA 2 spec, so you can actually look at the ISA and see this, and probably see it, I think. Can you see this? If we can. Right, memory descriptor, that's not what we want. Oh, text buffer descriptor, here we go. So this is basically it. So for a buffer, you got a base address that takes up 48 bits, and then they have the stride in the buffer, which takes up 14 bits, and they've got this thing called a cache swizzle for some reason. They've got these bits, right? They have these a format enumeration if it's a textual buffer, yeah. So, but then the texture one is bigger. So if you notice here, this is 128 bits for a buffer resource descriptor. But then for a texture one, so for a texture resource, it's actually a lot bigger, is it? Maybe is it the same size in Arduino 2? Oh, ray tracing contents. That's not it. But yeah, it'll be somewhere in here. Anyway, they're basically like they could be different sizes and whatever. So now we know like basically what the underlying form actually is. It's a little bit less harder to understand the stuff on top. The problem is when I tried to learn what descriptor set, a descriptor layout, and a descriptor pool is it's very hard to map to what these things actually are underneath. But so this is why I tried to explain it from the get-go underneath. Yeah, push descriptor is a good way of solving the problem, or going fully bindless, which we're doing. Hey, Davros. Yeah, man. Going all in. Custom engine. Yeah. We're not really doing an engine, but yeah. Custom engine for a game. A specific game. So in Vulkan, if we take a look at the headers, you've got a few concepts when it comes to this thing called a descriptor. On a VK video, get that out of there. Vulkan core. So if you look for the word descriptor, you've got a few things. You've got descriptor set layout, you've got descriptor set, and descriptor pool. So what descriptor set layout is it effectively describes what descriptors are in that this shader uses, but it's the layout, right? It describes what their types are, how many it's got, what their bindings and everything like this. So if we were to have like a few textures, maybe you have like, I don't know, noise, I don't know, maybe you have like some skin texture for some reason. But anyway, you have them on different bindings. In your descriptor set layout, when you make it, you'll effectively say, hey, at binding 0, we've got a texture. At binding 1, we've got another texture. At binding 2, we've got another texture. And when you make your descriptor set, you allocate the descriptor set in Vulkan. It will give you a handle, like a descriptor set handle, which allows you to poke the texture, the texture from the CPU into GPU memory in the GPU memory for this descriptor set. Now you want to be careful when you do this, because if the shader is using that descriptor set and you poke it and update it, it will cause race conditions and you'll see glitches in your rendering. And then the descriptor pool, and then to make things even harder, where you allocate your descriptor sets from is a descriptor pool, and these descriptor pools are like, yeah, it's really like, if you dive into the problem of using the traditional binding model, descriptor pools, descriptor sets are a nightmare, and there's no good general solution. But there's okay specific solutions for the way you've architected your game, for instance. Typically, I would say, like, it's just a pain in the butt, basically, these two things. But since Vulkan 1.2, there's been a new thing that's came out, and this is what HCC really dives into. So you'll notice here that we effectively just pass in our textures via these bundle constants, which are called push constants in Vulkan. And what these things are is they're like 64 bytes of constant data that just gets uploaded in the command buffer, and then you can read that out and start using it. But obviously, you remember seeing earlier that we saw like the buffer descriptor was like 16 bytes. So this thing isn't going to be 16 or 30 bytes, is it? Well, no, because what we've done in HCC is our textures and buffers are secretly indices behind the scenes, and the descriptors still exist. But instead, with bindless, you effectively you can have arrays of descriptors now. So we can have all of our textures and all of our buffers just simply exist in these massive arrays. And every time you use a texture, it will, like, the way the compiler will do it is it will go and fetch using the index and get the descriptor, then start using it. But it's only going to do that once, because the optimizer will come in and optimize that out. But so effectively with bindless, it allows us to really cheat and cut down the problems that you will find if you start using descriptor sets and descriptor pools. You effectively have to like manage all these descriptor sets and pools, and it's a complicated problem. But if you use this new thing called bindless, what it allows you to do is essentially only create one pool, and you create two descriptor sets from that pool, and you effectively have one descriptor set that the GPU is using, and the other descriptor set that the CPU is updating. And then the next frame they will swap around, and then the GPU will use the one you've updated, and the next frame will be the old one from the previous frame. The GPU will get reused for the CPU to poke more in. And this way it cuts down managing descriptor sets and descriptor pools to a very simple problem. And it also means that HCC can be designed in a way where setting textures and everything is as simply as just passing data to the shader, right, as opposed to binding descriptor sets, which is another thing we're just going to gloss over. So that's a very high level overview on what descriptor sets are, and kind of ignoring how much of a pain descriptor sets and descriptor pools are using a binding model. But if you really want to see how much of a pain it is, just try and do it yourself. But that should be enough information to see what we're about to do next. Hey Sockham, how you doing? Maybe search image instead of texture. Oh yeah, that's another point. Yeah, they could call it an image, but I did see the word texture in there. I just added car physics to my game engine. Nice. That sounds pretty complicated in a very simple way you've said that. Cool. Have you got all these different joints in the car, or is it more of like, or is it very rigid? How to use SDK for an engine? I'm not sure what you mean. What SDK? Like, we're using Vulkan. That's an SDK, I guess. But yeah, another thing I kind of forgot to say at the start of the stream is we'll presume if we get Vulkan, as soon as we get Vulkan up and running, we'll be doing a Windows stream where we port this over to Windows. So for people who are following along on Windows, it will have a working version after that stream, basically. Right, so we can now carry on down here and we can get things going. So HCC, because it's fully bindless and everything like this, it provides a great helper utility to just get things going with the descriptor sets. So it's called interop. It's pretty cool. We should just have to include this, and effectively it gives us a way to set up the descriptor sets. It will set up a descriptor set layout for us. It will set up a descriptor pool. And when we initialize this thing, we say how many descriptor sets do we want, because the format is always the same. So we're going to say we want 2 because we're going to double buffer them. And it will give us back everything we want. And we can start using this, which would be super good. So let's get using it. I want to include the HCC in, oh my days, wrong one. Interop, HCC interop, Vulkan H, Vulkan C. Include that there as well. Nice. we have anything else in here that's useful? We actually need that in the internal header. All right. So to set this up, it should be pretty simple. So in our global variable, we have all of our state. We want to store this interrupt stuff. Yep. So we're going to store this HCC interrupt here. This is what we're going to instantiate. So we're going to call HCC interrupt address of GP VK HCC interrupt. We need the setup structure. To get all the bells and whistles passed in. So the bells and whistles we need is all these guys. So we need our device passed in. We need an out pointer for the descriptor sets. We need a number of descriptor sets, G, GPU, VK, VK device. Thank you very much for the follow. Welcome. So we want a number of descriptor sets. GPU, VK, descriptor. See, basically it's like the number of frames in flight, I think we might call it. I call it active frames. One built by the CPU while one is being ran on the GPU. So we need an array of VK descriptor sets. Something like that. I forget this already. VK. Hey, Benham Turner, how you doing? Welcome. The suspension arms, yeah, just vertical ray trace on the wheels. Oh no, my tea. It's not cold. It's kind of just about warm. Will you be using descriptor buffer at all? No. Hey Philip, welcome. So the thing is about VK extension descriptor buffer is it only came out like 6 months ago now? Well, no, November something. Yeah, so 7-8 months ago now. And if you look at the device support for it, it's basically got no support. And they came out, Kronos came out, and they threw all this, like, this is amazing. This will be like the best extension ever. And it's no devices support it. So, by the sounds of it, it's really great for people writing a translation layer for DirectX 12 to Vulkan. Because basically the descriptor buffer is very similar to kind of DirectX 12's the descriptor heaps, pretty sure. Yeah, so basically when you set up like when you throw away the old model of, you know, making all these descriptor sets and using loads of descriptor pools and using Vulkan 1.2 style of working with these descriptors, it's like the API setup code is a bit weird, but when you have after the initialization code, it's basically fine. Like the descriptor buff thing is nice, but it's not there yet with support. Do you have any HTTP CCC file yet? No. So I actually went and standardized on that language name that Kronos wanted me to have for the C compiler. And I got the enum number 8, and I ended up making my own C variant. And it's very egotistical. I ended up calling it Hero C. So it's a thing. I got my own variant. I'll show you. Got my own variant. Let's prove it to you. Look, there's me. There's me, look. Ah. It got in there in the end. Hero C, number 8. Source language. It's in there. I still gotta plug it in my compiler though. But yeah. they didn't want me to use C because C is a very... Yeah, technically I have my own extensions or whatever. Yeah, I got 8 though. 8's a good number. Right, let's say we're gonna have like, I don't know, maximum of 256 descriptors. What's our bundled constants max size? We should make that another constant rate. Where is this thing going? Yeah, so in here, define GPU capacity. So let's say 64 bytes for now. You can always change it. So that's the maximum like size in bytes of constants that we can upload to each shader when we dispatch it. And what shader stages do we want? Shader stage compute, because we're only doing compute, right? No, there's no other shaders that we're doing in this renderer. That's the plan. So interop, boom. So that's set up all our descriptors, right? Should we take a look at the code? Because for people not familiar with Vulkan, let's just have a look and see what it actually does under the hood. Now it's going to be all these errors in our face, but anyway. So the way HCC works is the descriptor set layout. Let's go and read the docs. I made some good docs, you see. Integrating into your engine. Let's first one into the web browser. Web browser's good at this. No? Oh, that was a compliment. There we go. Here we go, bindless resources. So the descriptor set layout is effectively binding 0 is for storage buffers. So just for buffers, we've got an array of 256 buffers. Then we've got another array of 256 images of binding 0. These are sample images, the ones that you sample from. Storage images, which are ones that you only just load and store from at a unnormalized coordinates. They're at binding 2. Then we've got samplers at 3. Now, all of these actually overlap. Wait, do they? What was the reasoning for this? Do they overlap? Oh, no, no, sorry, they don't overlap. Yeah, yeah, yeah. All of these overlap, meaning that like there'll be wasted descriptors in the middle. So we're gonna have this thing called a resource ID, where like a pool of resources, and the type could either be a buffer or an image. So we're gonna use that resource index to fill in the the array effectively. So there will be a wasted space with this solution, but it'll be okay. So we go over. So we go over all the bindings that HCC provides. Yeah, so we have storage buffer in 0, sampled image in 1, storage image in 2, and sampler in 3. And so we can look up and translate that into the descriptor types like so. We set up an array of these bindings for the descriptor set layout, and then we create our descriptor set layout. Now we have to do some extra funny business in here. So we have these bindless flags. We have to do like an extra bit of like create information that has to be bundled onto the pnext when you create this descriptor set layout thing. Yeah, it's not the most smoothest code, but you effectively have to set like partially bound, meaning you don't have to set every slot in the array, because if you by default Vulkan wants you to set every slot in the array. And you can also update the descriptors after you've bound it in the command buffer. So we've got a couple of flags there. So it creates your descriptor set layout, and then we request 2 descriptor sets because we only need 2 descriptor sets, one that the CPU updates and one that the GPU uses and renders from. Heresy, no way. Yeah, I had a chance to call it HCCC. I didn't quite do that. I decided to go the more egotistical approach of naming it after myself. But anyway, what do you think about the current BS ideology, minimalism, web design? I have no idea what that is. Thank you. I know, right? It's a good achievement. It's cool. Oh, let's get that Pepsi Max open. So yeah, after you get your descriptor set layout, which describes. Thank you for the follow, appreciate it. Oh, no, it's a raid. Robot, thank you so much. Welcome, raiders. How are we doing? We're currently on a new project right now. We're using our shader compiler. We're running a game without an engine now. So hope everyone's doing good. How's the stream, Provod? Thank you. So we're currently like day 2 of this. We're just setting up Vulkan. Day 1 we spent basically opening up a window and getting things in order. And we started on the Vulkan as well. But yeah, we're just carrying on. So I think we can look, here's our game right now. It's just a window opened with X11. But yeah. It was nice. We deleted a lot of code. Awesome. Sounds like a successful stream. It's great when you get rid of all that code that you don't need anymore, and things are just more simple and easier to understand. Awesome. Was it a refactor of any of the Vulkan code, perhaps? So after we have our descriptor set layout, we effectively just make a descriptor pool that has enough descriptor sets in it for the descriptors that we need, and then we just basically allocate those 2 descriptor sets from it. Because it's bindless, we just allocate the 2 that we need, right? And then we store them in the out pointer that the user passed in. Oh, then we also set up this thing called a pipeline layout. Yeah, pipeline layouts. Boy, explain these. Not directly Vulkan, but stuff that feeds into it. Oh, okay. Right, so like the render graph probably. Right. Or the render pipeline at least. Cool. Yeah, that stuff can get really complicated. Yeah, it's a lot of work. Thank you so much for the follow. Appreciate it. Yeah, so what a pipeline layout is you need this to go in with your pipelines. Effectively, it just describes how big are your push constants, and it wants to know the layout of your descriptor set, so it can effectively like figure that stuff out when it invokes your shader. Yeah, so luckily this stays the same because we're using binderless now. Like in the old school binding model, you would have to like manage these objects as well, like big pain. So we luckily get rid of all of that now, and we have HCC basically have this nice interop layer which creates all of this for us. Right, so that explains all of that. So now we've done this descriptor star section. That was good. That was a complicated one to describe, but I'm glad we got through it. I hope people all understood it. So what do we need to achieve next? So a good thing to have would probably be a swap chain, which would be next. So let's go and talk about what a swap chain is. So when you render to the screen, like you need an image. So in Vulkan you use, I don't know what happened there. So in Vulkan you use VK images, which is basically a texture, and you kind of render to these things. And the swap chain allows you to get an image that was created by the display manager, so X11, and then you can write to that and it will composite that to the actual back buffer, or if it's full screen, it will hopefully go directly to the actual, well, it will skip the compositor step basically in the whole chain of what goes on at the lower levels. So we need to create this swap chain object, and you need to create it, and it needs to be changed when you resize the screen. It needs to be recreated when you resize the screen as well. But if we dig into the HCC code base, we've made this earlier. I just want to nick this code and get it going really. But I think we want to make another function because the wrong one. GPU, that one please. Yeah, I want to add a new function which is going to create I called it swap chain and friends before. It was a good name. But you want to create with some width height. Yeah, we might stick with this. It's called and friends because you need to create some. Why do we need to destroy them? I think we destroy them because they could be in a state where. Yeah, alright. Let's take this with us. Cool, I think we need a boolean there. Right, swap chain and friends, this is a good name. It's a good name. So, width and height of a window. So we need a way to get like the size of the window. Because on you know what? Yeah, because on some platforms it might you might not be able to query it. So I think we'll have a way to reach in and get that, but for now we'll hard code it. I think that's a good shout. Window width 800 by 600. That's what we're rolling with for now. So window width, window height. To get this from the OS. You know, maybe we don't need it passed in. Maybe we can just do the call directly in here. Yeah. That's a good idea. All right, let's take Benny Montana. Enjoy your food, sir. So what we want to do is just go over exactly what this does. So anything GPU, whatever, has to be replaced. So let's do a find and replace. I learned this from Perry. I didn't learn this. I don't want to upset Perry, so I'm going to do a find and replace this way. GPU VK dot. There we go. Like a true Vim expert, like I am. Put void in there, otherwise I'm not a real C programmer. So, what we need to do is we need to have a VK image. Yeah, I think we kind of want to... Wait, first of all, let's sort this music situation. I think Stone Rebel released a new album, so I want to try and play this one. Let's go and give this one a jam. I wanted to listen to it, so I didn't play it first. So, typically you get back an array of images. Should we dynamically allocate these, or... Yeah, I think we'll just do a big number for now. And let's just say 8. Like hopefully it doesn't crash. You should only get like 2 or 3 back, but I think the Intel driver gives 5 back for some reason. It's really weird. So VK swap chain images. These are images we'll get back. And then what we need to do is we need to create image views. So an image view is essentially it's a way of accessing the sub resources of an image, but you always need to use an image view when you refer to it in a shader, or like whenever you refer to an image, you always access it through the image view for the most part. So you always need these things. So we'll go over that in just a second. Cool. So VK. Thank you for the follow. Appreciate it. Welcome. Also need a swap chain handle. So if we have a swapper chain, what we're going to do is we're going to wait for device idle. Now this is actually a really bad way of doing it, but we haven't got anything working, so it's a good way of doing it. This will wait for the GPU device, for all your work on the GPU device to be finished. If you have multiple queues of things going on, this is bad. Yes, this is actually quite bad, if that's the case. Typically, you would just wait for the queue that you submit graphics down, or the main queue that you do your main compute work on in this case, right? Because we're only doing compute shaders. you would wait for that one to be done with the swap chain. So as soon as it's done with the swap chain, then we're not going to give it any more work. And then, so typically we'll wait there for it. What do you mean a game without an engine? Do you mean like playing baseball outside? No. That's a good joke. Basically, we run a game from scratch and we're not using an engine. Yeah, exactly. So no game engines. Hey Don, an engine is this, Don? Actually, I won't play it again. I'll save it. I wanna make it very special. Hey, very much. I'm writing the bare parts of the engine that you need specifically for this game, but it's not a general engine, so it's not So it's not very marketable, basically. 2D replace with swap chain with wait for timeline semaphore. Instead, wait for timeline semaphore to tell when the swap chain. Well, not even that. Maybe times. Okay. I think it might have to be a fence for when the present is done. Or something like this. Wait on the fence or semaphore for when the swap chain. It might be a semaphore. Yeah, it might be when the key present has finished, I think. Yeah. Being presented, some of them. Yeah, that's the better way of doing it. Right, so we can go over and destroy all the images. So again, we need another thing in here. U30 VK swapper chain images count. Very easy to misspell that word. Cool, so go over all the images and we then destroy them using VK destroy image view. We'll create these in the future. We're kind of just, yeah, doing it the wrong way around, but anyway, there we go. Cool. Very good. So typically it would be a good idea to clear these out to be a null, you know? That'd be a good idea. How's the C compiler going? Well, we've completed it enough to start using it. So this is why we're doing this project, is so we can get to using it really quickly, while I'm also testing out an idea that I've heard from people for a while, is you shouldn't use engines, and like you should write engines or write the code specifically for the game and not use engines. So I want to try this idea with actually testing my C compiler, and this is the fastest way to do it. So it's really a good combination of that. Plus, I just want to also stream it so people can watch writing something from scratch using all the latest and greatest technologies. Also, while using a very old programming language, but there you go. Oh, we need a surface. Right, this is good. This is good. Yeah, we'll get there. Right, so we need to get this thing called surface capabilities. So surface capability basically tells us it queries the information from X11 in a very, like, effectively a Vulkan surface, a VK surface, is a little handle to your window or your full screen window, that it can talk to the display manager, so like X11 or Win32, and it can be like it can query stuff about it, and when you create the swap chain, it's like bound to that surface, right, and that sort of connection, right, to that window, and those images are obviously in with that thing, right? So when you get the surface capabilities for the surface, you're getting like, hey, what is the minimum and maximum number of swap chain images it can have? What's the minimum and maximum size of the window? But also, what is the current size of the window? And there's some other bits and bobs that we can kind of ignore, I guess. Or okay, no, let's just explain it. So support transforms is like basically orientation, like landscape, like like rotating it in 90-degree angles, and I think flipping it as well. You can do that, but we're just going to keep the default, obviously. There's composite alpha, which basically means you can say, hey, if there's alpha left on the swap chain image, make it transparent. Or you can, it's up here, look. You can do opaque, pre-multiplied alpha, post-multiplied alpha, or... Wait, can you do that? Maybe not the transparent thing. Maybe I lied. Could you do that? Yeah, maybe I lied about that last bit, but I haven't really done that too much. So yeah, but effectively you say what format the alpha is in for the compositor, I guess, and then it can work with that. Usage flags. This just says like, basically it's like we're going to check these usage flags and we're going to say, hey, can you write to this from a compute shader, which is going to be storage, which is supported on basically all devices, but we'll check anyway for completeness sake, right? So that's surface capabilities. We're going to start doing stuff with this now. So one thing about surface capabilities, which is like super annoying, is if width is set to the special value, the size of the swap chain is set to the size of what the window currently is, or something like this. So we're going to have to get this from the operating system layer. So window, I think we'll call it window size, so unit 32 times 2, window size, and we're going to say OS window size. And I think sometimes on Windows it actually gives you this and you have to handle it. But other than that, you can just use whatever the fetch data is back. Like maybe in full screen it might let you... Sorry. Yeah, if it's set to this special value, the size of the swap chain is set to basically whatever you decide. Whatever you provide it, I think. You know what, let's read the docs on that. So I'm not just... Wait. Surface capabilities. Indicating that the surface size will be determined by the extent of the swap chain targeting the device. So targeting the surface. Yeah, so I guess this would mean whatever you pass into the swap chain extent when you create the swap chain down here, it will be set to that. Bear in mind it's got to respect the min max sizes of the capabilities. So we're going to get the size from the operating system layer. We'll get that in just a second. Then if it's 0, meaning it's like minimized on Windows, it does this, we're going to return false. Because the way we call this will be handled in a certain way. We keep the swap chain size around, and the reason why we keep that around is what do we keep that around? I think because we check if it's changed, and then if it has changed, we'll trigger a resize, something like this. How do we do that on the other one? Oh, no. We just use the swap chain size when we create the viewport in this case, but we won't be using viewports and scissors. But we'll still need it. Yeah, we'll need it for rendering code. So we'll essentially just call it u32 times 2 swap chain extent.x swap chain extent.y. Cool. Right, so after you've got these things ready, we can now actually create the swap chain. Now, actually, we should have destroyed the swap chain. Yeah, I think X11 prefers if you destroy it manually and then create it again from scratch rather than reusing this old swap chain. Have I played the System Shock remake? No, I haven't. No, I've not played the System Shock remake. Is it good? Disney game took 6 years to make. The original System Shock took 1 year. Oh wow! Wow! Yeah, that's crazy. I do not know why it took that long. Like, game development is complicated nowadays. Like, as you can tell with Vulkan that we're doing here, game development is complicated for many reasons. But yeah. Right. So what we kind of want to do is destroy the swap chain manually. Because I think not DirectX, I think X11 prefers if you do this. I think it prefers if you destroy the swap chain. It's really weird, because we had a bug before. If you kept resizing it, it would crash. Something like this. And even the VK Cube example, I think someone was saying does this. Why does it destroy it again? Let's have a bit of a think. Right, so the plan is to destroy it first, not do this. Again, I can't tell you the exact reasons, so don't take this as the way to do it. Alright, this surface, we still need to make the surface. We need this surface format. We'll go over this in just a bit. Let's just, actually no, we'll go over it now. So you need to provide a lot of stuff in here. So the surface format, all right, what is this? So basically there's, on each platform, there is a format that is supported across every device. Some devices support more formats, but there's basically a format for each platform. So you just, there's one format for standard sRGB, RGBA 32-bit per pixel, right? There's a standard one for that. And then there's a HDR format typically as well. So what we want to do is just use the one for the platform. So on Linux and Windows, it is this. So we are going to have an ifdef in the code base, but that is fine. We will have ifdefs, right, in some parts of the code, but in the GPU code, because it is kind of a platform abstraction itself. So that is fine, but so it's only really. Well, why am I doing that? It's like I'm at work. Oh, it is. So we have a OS. Wait a minute. What do we call it? Core OS. There we go. If defined or Windows. This is very good. We're gonna play with strange. Oh, they made it in Unity first. Oh, right. Oh, wow. Only to backpedal and do the whole. Wow. Literally do a remake. That's crazy. But it's great that they finished it, though. Yeah, I remember when it got funded, actually. I have a brief memory of it. I never played the original, though, so I'm not going to pretend like I know. Yeah, I think I might pick it up. What platforms is it on? Is it on PS5? I need a new PS. I need a new game to waste money on. Not really. I've got plenty of old games to play still. Yeah, so like if you go and like do another platform, this will probably be different. Let's keep it separate because maybe the HDR formats might be different. I don't know. Maybe they'll be the same. But anyway, there you go. So we're going to use this format here. Radio. Jobs are good. So what we need to do now is actually create the swap chain. We will create the surface in a bit, and we already spoke about what that thing is. Right, we'll just it's very simple to do it. It's kind of like an OS thing. Swap chain images count. There you are. Very good. Oh, not core assert. GPU VK assert. We don't malloc anything because we're not a bunch of scrubs. We just we've got it allocated like this. We just have 8 because hopefully that's the maximum. I think in future we'll temp allocate it, but yeah, not using malloc though. It's only because it came from a sample program that it's had it in there. Right. Oh, I wanted to copy and paste that. Did I? Oh no, it's the views. Right. I see now. Wait a minute. Oh, okay, it was getting the size by passing in null. And then it was getting the size out, and then it was getting the full. Right. I see what it's doing. Because in Vulkan, if you have something that takes a count in as the second last argument, then a pointer as the last argument, if you pass in null for the last argument, it only gives you back the size, so you can then allocate and then call it again, and then get it populated with the proper stuff, which is a really cool design. But well, it works. I don't know if it's I have no opinions on. It works well enough. I think it's good. This doesn't return. Oh, incompatible pointers. Right, get rid of that. Cool. So now we go over all of the swap chain images and we create a view for each of them. right? Did we? Oh, the image usages. We didn't. Oh, we just want storage, right? We're not copying. We don't want storage. We should assert. Where's the capabilities? Core assert. Surface capabilities. Supported usage flags and VK usage storage. So storage just means. Wait a minute. Why isn't this? Oh, image usage. Yeah, storage just means they're using it in a shader, like the image in the shader. So it's a compute shader, just use it in there. So missing storage image support for swap chain. We need this to write from a compute shader. So I guess we'll make that a little bit cleaner, right? We'll just bring it down to another couple lines. So, dun 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 dun. So we go over all the images that we get. So we create the swap chain. We call this function called getImages. It populates those in an array. So now we've got all this possible swap chain images that we could render to, and then we will present. So we'll render for one image each frame, and each frame will be a different image, and then we present that at the end of the frame. Now we go over all the images, create an image view for those. An image view, remember, is a way to sort of like view a sub portion of it, so you can view a sub MIP range or a sub array layer range. Obviously there's no MIPs or array layers here. You can have array layers, I think. Yeah, you can have array layers for swap chain images, apparently. So again, we're keeping the same format because it can also reinterpret the format. The swizzling stays the same. So it's basically just a 1-for-1 match to the original image, this one. And then we're going to say VK swap chain images goes in as the image we're viewing. And then it's a view type of 2D. So nothing has changed. Literally nothing has changed. Now, we want to create that lovely view and then stick it in the array of views, image views. This has a depth image that was created alongside it in the HCC sample, but we don't need a depth image. See, this is what it's like to create an image in Vulkan. You have to do this big structure thing, fill it in, create image, allocate the memory and everything. So this is what the driver's doing, but the X11 stuff is probably doing behind the scenes, is creating an image and allocating the memory for it and stuff like this. Yeah, and then it'll create a view. No, it won't create a view for it. But yeah, we create the view manually ourselves. Just delete that. Now we need some semaphores. Good thing about this one. PC for now, planning recent consoles. But no specifics. Wow. Crazy. All in all will be even longer. That's a lot of dev time. We write the image in the shader and then present it to the screen. Yeah, so we write it, we've got a shader already, it's here. We're just clearing it using compute. So we just write to it. Right, it comes in as a write-only output texture via this, and then we essentially get the coordinate for the dispatch with the dispatch index, and we clear it to red, right, and then we store the color in there. So that's what we're planning on trying to get up and running first. But yeah, still a bit to go. So semaphores are things we end up using. For now, we're just going to comment this out because we're not there yet, and I would just be pulling out of thin air. So we're just going to comment that out and leave it there to copy and paste for later. So this is now basically done, but we've added a few platform thingies, and so we need to sort those platform thingies out. So we need a way to get the surface, right? So before we create the swap chain and friends, we need to create the surface. So the surface is actually really easy to create. There's a couple of functions you can, headers you include, and it does all it has the interoperability code with the display managers. Core OS Linux. Let's make it easier to set that up. So we need to. Oh, we need xlib. Ugh, trash. Right, that was the wrong file. GPU. Right. So it wants to know about xlib here, but effectively, right, you get your I think maybe we can, when we include this header, we can put a couple of defines in to avoid knowing about this stuff. But yeah, you need your X11 window, which is called window for some reason. You need this display pointer, and you have this create information, and you create a VK surface from this. It's really simple, but you need the X11 bits to get passed in, and this will. I think this is implemented by X11 itself, and they give you back a surface. And you can also get back this presentation support thing as well, which we'll probably need to use. Oh, wrong one. Yeah, xlib, that's right. Yup. Good old xlib. So let's type def some things. Now, I don't know the actual type of xlib of window, I think. So we're gonna do some investigation. User include x11. Grep for, I've done this many times before. Maybe not. Right, I can't quite find it. So basically, I think we want to look for like define. Define star dot star. I think it's regex, right? Window. Oh no, define window as something. Right, so card 32. Card 32 sounds like it would be a 32-bit integer, right? We live in hope. I know this is a type def. I've looked for it before. Int or long in this case. Let's have a look at it. Vim xmd. I'm pretty sure it's 32 bits. If long 64, right, then if the long is not 64, it's that. Okay, good. Just to make sure. So I think what we can do is we can type def it. as a U32. And then it's really bad. And then it saves us including the xlib header. Because we only need the bare minimum. And then display, we can just say it's a void pointer because we never actually use it, right? So we can type def void void display. Then visual ID, let's look for that one. Card 32. Cool. As if printf in here. Ugh. Stings. Just include standard IO just to shut it up. Remove standard lib. Yeah, void star's the way. Love a good void star. Right, so we'll say here, like, you know, Vulkan xlib only needs these types, so just forward declare them to avoid the xlib header. Right, so that's super cool. So what we can do is we can now create the surface. So we're in the sample code that I've got from the sample application for HCC here, and we're just going to nick this. So again, it has more if-def code, but again, it's super small. So swap chain and friends, put it just above there. If defined core OS Linux. So where do we get these things, right? Where do we get our instance? Where do we get our where do we get our display connection? Where do we get our window from? So we don't actually have those yet. But if we go to the source os.h, we can add these things here. So what we want to have is like, see what I do for that visual ID. Oh, visual ID from, oh, do I need the xlib header? Maybe I can forward declare that. Then I need a screen. Right, okay. Right, we'll just include the header then. Oh well. We'll get to that in a minute. So we want like OS, window, like backendy bits, right? Backendy bits. So we just want to do like void star for what is the instance, I guess. And then the actual window. So there's a window handle. See, instance is like a Windows terminology. We can also call it connection. But yeah, we want these. So we want to say, hey, can we get OS window backend for me, please? And we'll fish that out. Oh yeah, we want it for a certain window, don't we? Right? So we go to the implementation of this, which will be in OS Linux, and there's obviously one in OS Windows, which we'll get to in a future stream. But for now, we just need to get something actually working. Then, so what we're going to do here is give them, so there's like an OS internal bit, Linux internals, Well, so we don't have multiple windows set up yet because we're just getting things set up. So, but there is like some built-in X11 window here. And there's a connection here as well in these globals. So we can just reference that. So we create this backend thing. Backend. No, let's just do it this way. So dot connection equals G OS Linux dot connection. Then window, which we cast into a void pointer, and we cast up to a U pointer because it's a U32, right? In window X11 window. Sure. Core unused because we've got unused. So in the future, obviously, we'll fetch a window from a pool and then take a look at its data there to get the actual window handle. But for now, we only have one. Cool. So there's our backend window. So we can now use this super lovely thing here. We can say, hey, get me the OS window backend equal OS window backend, pass in the window ID. What is the window ID? Good question. So we can't need that passed in. Yeah. You know, also we could just hard code it. I'm gonna hard code it. I'm gonna specifically hard code it as null. So when we actually make it properly, it's gonna crash. So I'm specifically gonna make it as a null handle. Then we properly handle it, it's gonna crash, and then we can actually correct it properly. So this means I don't have to change parameters in this GPU initialize function if I have to move this stuff around anyway. So that will be a good help. And it's a backend, like a Wally. So we need to include OS. You know what? I want to do something else. I want to go to those compiler flags, and I want to do another -i and say, hey, source is in the. So it means we can just do this now, like that, right? That'd be super good. So we should now be able to go down to here again. Window backend now all compiles, which is super nice. Throw in the connection, cast it to a display. Then a U pointer, then a window. Oh yeah. GPU all kind of set. Oh, I need to do this find and replace. What's this instance thing? Ah, yeah, the Vulkan instance. Yeah. VK surface, we'll get that all set up. Then this window. So we need to actually include the xlib header here. It sucks. But anyway, we'll do it. X11 xlib. Yeah, so one thing to note actually You remember last stream when we made these extensions when we create the device, or the instance, rather. See, we've got this sort of like KHR lib surface here. You have to enable this extension as part of Vulkan if you want to call the function we're about to show, right? So this function here, this create xlib surface KHR, actually is part of that extension that we enabled last stream. Let's just quickly get the tunes back up and running. Hey, we've already played this one. Oh, we go. Right, so we actually need in the Vulkan backend global thing that we have here, because globals are the best, we need a surface now. So obviously if you have more windows, you need more surfaces and swap chains. And remember that surface is Vulkan's way of saying it's a connection to the window, to the display manager's window that you're rendering to. And the swap chain is talking about is the actual allocation of the images to that connection for the window, right? And then you interface with the swap chain to sort of get your next image to render to, and then you render to that image and then present it. So that's fixed a lot of errors there. Q family, eh? Ooh, get xlib presentation support. Man, I was on it when I wrote this code. Window backend connection. Right. So the thing is, this could crash, actually. We actually need to go and seek and find, you know, we need to actually go and seek and find the a presentation queue. You know, why don't we just use the graphics queue, even though we're only doing compute? There's no difference. Yeah, let's change that, because so effectively, like the presentation, like the queues that we made with our device, they could have, there's a third thing they could support. So there's graphics, compute, transfer, and present. Present is not necessarily a queue bit like this. It's not one of these sort of bits that you can simply check. You need to talk with the display server, the display manager, whatever you want to call it, and ask what is that presentation queue for some reason. So I was first going to try and look for one that isn't a graphics. Doesn't have graphics, because we're not using graphics support. But the one with graphics basically always, like I haven't seen a device without, like that has graphics support that doesn't support present. So we're just gonna, I think we're going to undo what we did and just search for this one. That's the way we roll there. So then that means our presentation support that we search, that we do check here, it will, I wouldn't have to move it up and search for a queue with present as well. We can just stick it in with the xlib code down here. So that'd be cool. Then there's the Windows side of things. So this one is GPU. This one is core set. Then this one will be VK instance, VK surface, VK physical device, VK queue, and then we'll do a, we'll clean this up here. And we want to use our super lovely Core OS Windows. Hey Meeple One. No, mine's not a VRR monitor. Is that a variable refresh rate? No, it's an old, like 10-year-old 1080p 60 hertz monitor, 22-inch. It's really not anything special. Um, I could change it and go for something better, but the issue is as I go for something better, then I'll have to stream like down sample. Let me go for a 4K one. I have to stream a downsampled version of 4K, and I don't know how well that will look. Maybe it looks better because it's a downsample, isn't it? Maybe. So maybe it might be okay. But yeah, and also I'm trying to save monies right now because I have a just moved house and got a baby on the way. But yeah, so there's life things that are more important than a than to than a better screen. Yeah, I'm just trying to. We're just yeah, the wife is pregnant. Yeah, we just got a little Moses basket set up next door now, so it's feeling real. So yeah, baby's due in 2 months' time. So yeah, gonna be here quite soon actually. Um, hopefully there's something in the works at work where I should get some, hopefully a promotion. So hopefully that will come in and help out with that situation. That'd be very good. When I used to stream, my stream was 1080p window of my 1440p. Okay, right. Yeah, I think it should be fine. Programming career will be fine. Fine. Yeah, I hope I do too. I hope I have a good. I hope I do a good job. Right. Um, you got to think back to when you were on the other side of that, and a lot, rather than referring to how you feel right now. A lot of the time, like how was you back then, and how did you react to certain things, and to sort of be very open minded with that sort of stuff. Ah, thank you, son. Oh, you did a section of a monitor. Oh, nice. Yeah, don't worry, he will be. He'll be his first reading language would be assembly. Then don't you worry. He'll be getting books out the gate on you know, maybe we'll start on 6502, like a really simple one, you know, because it's a baby. Yeah, sounds good. Complete separate monitor. Hmm, interesting. Yeah, just be add. Yeah. More. Yeah. Yeah, hopefully it's like push or pop, then he'll get stacks from an early age. So what are we thinking about Vision Pro over here? Ah, interesting. Very interesting bit of technology, that Vision Pro, isn't it? Like like it's a very impressive bit of technology that they've pulled off. Like it looks really cool. But it's a lot of money. And I was speaking with someone at work, and I was like, this this is just crazy. Like I was just laughing. Like, how do they expect users to buy this when other VR headsets are quote unquote too expensive, and they've just gone and made it like 8 times more expensive than a standard VR headset? And he was saying, well, it's probably for like more of like an enterprise or industrial use where where like big companies with lots of money will use it to actually design very expensive things with it. Um, and that's probably going to be the first use case of it. And that makes a ton of sense, really, for that sort of thing. But and for really enthusiasts, I guess. But yeah, I think the ones where it's designed for an actual user is going to be much later. But yeah, it's going to be hard to how do you get users on it, because it's not really a mainstream thing. Maybe Apple could do it right. Maybe they could do it. It's not just it's a headset with embedded Mac. What do you mean by embedded Mac? Yeah. The headset's got a lot of technology in it, right? It's got like a whole M2 chip and everything, and that R1 processor. But yeah. Oh, it's got like an external battery as well. Oh, this sounds crazy. Oh yeah, I remember hearing it's a 2 hour battery life. It was like really bad. Like, oh. But then again, you don't want to sit in VR for more than 2 hours anyway, right? So, but yeah, you got to remember to charge it. You got to have like a charging station or whatever. Yeah. Yeah. 4K is the way. Yeah, but it's not really a computer though. It's very limited computer. You got to use your wrists to like do stuff. Like, and your eyes. Like, good luck programming in that. You'll be like staring at the keyboard and blinking to type. You know, it won't be good. You'll get really good eye muscles though. You'll probably have to see like a wizard. See around corners and everything with all those muscles you develop in your eyes. Right, so we've got a surface now and a swap, which means our swap chain will work. Let's have a gander. Computer says no. Right, we need an OS window size. So again, we'll do that. I think we'll do that very terrible, but future. But this will warn us in the future what the issue is, right? Thing here. Because right now we won't check the handle, since we only have one window anyway, but in the future we'll check the handle, and it's null, and then it'll crash, and we can fix it. So we're going to have a new OS thingy-majig. I love a good thingy-majig. So we want to return a U32 times 2. Oh, we can do this now. That's really bad, actually. Maybe I'll have to do it. Maybe I should move core into its own thing, actually. We'll sort that later. What am I doing? I need HCC. Wait, have I got HMaths in that compiler flags? I have. HMaths with an S. Multiple math. Types, please. So we get this vector2 type. Awesome. We want a size to come back, please. Thank you very much. Plop over here. How does one get the size of the window? Well, I think we stored it in that structure, right? So I'm pretty sure if we go over to source OS, OS Linux internal, we got the width and the height here. Bear in mind, I'm going to change this to a size. So we're just going to return GOS Linux .window .size, and then we're going to. Oh, we need to do all this here. When we open up a window, we should set GOS Linux window size equal width height to $. Size.y, there you go. Right, so that should be everything. Oh no, I just closed the wrong window. Yeah, so you see it doesn't have an error anymore. Bam. Cool. Right, so we go up to the list. Where's the list? So this is in the initialize function again. We've initialized an instance, a device. We've initialized a descriptor set, layout descriptor sets, descriptor pool, and a pipeline layout. We've got a surface. We've got swap chain and friends, right? What were the other ones? Did I delete them? Oh, I got trigger happy on the deleting apparently. So we still need semaphores, command pool. That's it. All right, let's just get the command pool. Here's one I made earlier. We're going to allocate our command buffers as well. Let's get these guys in there. So VK command pool. So as you guessed it, the command pool allocates the command buffers. You don't really specify how many you want up front. It's really weird. You just allocate what you need. Yeah, it's quite strange. So we put them in the global thing here. We need multiple command buffers, right? We need one for each frame, active frame, because remember, one is built on the CPU and the other one is ran on the GPU, is actually executed, and then you swap them around. So what we need to do is, oh, we've already got it in here. So let's do this. See, Perry, I can do find and replace. Look at me go. Oh yeah, I'm using all the new fancy NeoVim stuff, so I'm a typical Twitch streamer now. I'm in that club. Maths more is all the math. Oh my days. Yeah, the Greek name. Yeah, it's quite the name. Nothing to do with numbers. Okay. Well, compute shader directly set the data of the image that will be presented. Yeah, it will sets it directly in the shader. Hey there, Zaka. Welcome back. VS Code is typical Twitch. Right. Maybe. I don't know, VS Code is for people who... I'll stop there. So we create ourselves a command pool. And then we simply just say transient and reset command buffer bit. Transient means this command buffer gets recorded, it gets sent to the GPU, it gets used once, and then it comes back and then gets reset. It has that cycle. And then we enable the reset command buffer bit. Sorry, transient means it gets used once. But reset means it can get used once and then reset. Sorry, reset command just means it can just get reset. So both those together means it gets used once and reset. And so that helps the driver sort of optimize for a specific case. Cool. Next, we actually allocate the command buffers that we actually need. They're primary command buffers. You can have secondary command buffers that you pre-record, and then you can call a command that dispatches another command buffer from another command buffer, but we're not going to do that. It's pretty cool, but we're not going to do that. Yeah, when people say the word cool when it comes to programming, you always got to be skeptical about it, because just because something is cool doesn't mean you should do it. Because cool often means it adds complication. You typically just want to solve the problem that you're solving, and not because it's cool. Not per swap chain image. You have one command buffer, we might need 3. We'll see how it goes. We might need 3. Yeah, if you double buffer, yeah, it might be actually. Yeah, if you double buffer your swap chain, you need 2. If you triple buffer, you actually need 3. Because the command buffer isn't finished using until the present happens. So your command buffer could be... Yeah, it's complicated to explain, but... Yeah, you could typically... You'll have 2 command buffers that are on the GPU. One of them is being waited to be presented, and the other one is being, I think... The other one is actually being rendered. So that, yeah, I wouldn't quote me on that, but we're just going to stick with 2 and do double buffering for now. Right, so there's your command buffers. We can start recording to those soon. What is next? What is left? We need semaphores. We had semaphores, command buffers, swap chain, descriptors. We needed 4 things, didn't we? Yeah, so we need semaphores now. Sweet. So now we can actually start doing things, I think. So what we want to do is probably test that this thing still actually works. So we want to do a printf and just say woohoo, like Super Mario does, right? So we press F5 to compile. We compiled. Then we want to cd to the workbench and game without an engine. And what we're going to do is we're going to then run the game. Did we get a Vulkan validation error? I think we did, but our Vulkan error handler is not set up to be decent at it. Let's print out to the terminal as well. Yeah, I think we might need a fence, but you can use these things called timeline semaphores nowadays. And I want to try and use them in this project because I've not used them yet. So if you enable the Vulkan validation layers, you can get this stuff to show up anyway. But the beauty is we've also added a stack trace element into this. So it also gives us a stack trace. So, which is pretty cool. So it tells us exactly where it is. Well, not exactly, you got to refill the garbage, right? But this is where this is our error handler, which we use the debug utils extension. The debug utils, yeah, VK debug utils extension. And you can set up this error handler and you can do stuff, and we have some custom breakpoint things, so it breaks in the debugger and you can start having a look. Or it also prints out to a file, and also, yeah. We could disable this one for now, but yeah, I don't know. We'll see. Anyway, prints out to the terminal. So what we can tell is we look far enough back. In the initializer 247, we'll find the problemo. So the problem is that the window is 0. So obviously, in the OS code, when we opened the window, we did a silly, and we didn't set the window handle. That we got when we created the X11 window. So we give that a recompile, give it a run. Why didn't that work? Where's Windows 0? Web engineering software is cool. Exactly. This is the problem. It's cool to engineer. Very. It sound. Yeah. Yeah. I think you should triple buffer. Yeah, triple buffer is a good solution. The swap chain images. When you make a lot of lists of what's required on Vulkan's side to achieve a simple compute setup for renderer. No, it's very. Yeah, I won't really make a list. Like the code itself at this commit will be that. Oh my days, I forgot to put a tag on the previous day. Should we do that? How do we add tags? I've not done this before. Git tag. Create an annotated tag is simple. Yeah, so we're gonna say like, I want to put a tag in the repo. Git tag -a day 1. So end of, yeah, and then message. Oh. Yeah, I was wondering if it does anything. You want to write a message for the tag? Right, end of stream day 1. End of day 1, something like that. So I do a git log. We got a tag. Look at that. Right, so now people can actually just jump back to that commit and view it from that day. Awesome. But yeah, I don't know. setting up a list would be a lot of effort, but yeah. I know. I think the code base will serve as the example really, because it's just going yeah. Um. Right. So why is our window like? What are we doing in the back end? Are we doing a silly? Right. We simply initialize the GPU backend before the OS. Is that right? Let's take a look at the sources. Ah. Right. Initialize open window. Then do that. Um. Yeah, we'll do that. Can always change it. Rightio. Okay, so in the famous words of Super Mario, we have a woohoo. So yeah, pretty good. So now we have a Vulkan instance being made with everything that we need. Now it's time to do the rest. Oh, tag day one would have been fine. Oh, thank you, Perry. Noted. Go for Patreon only, right? No, we don't have Patreon, but we do have. You can support via Ko-fi, and that's the best way. That's the best way for me. Like in terms of like the most money in terms of goes to me that way. But if you guys like the Twitch integration, you can also subscribe via Twitch, and then. But if you hop on the Discord and go to this channel here, the Game Without Engine info channel. Read the instructions there. It says like which way, it says like which one, or it says the two options. And when you sub via those two options, you just need to link your Discord account, and then there's a secret channel on the Discord, and it will tell you how to get access to the code, basically. But yeah. Cool. So this is our graphics API. So this is like our equivalent to OpenGL, but specifically for our game, right? So we've got to be able to get the surface resource ID. There's probably just going to be I don't know. That's probably just be 0 or something. We'll see. Yeah, it'll be 1 or something. Yeah. Anyway. So this command buffer begin, command buffer end. I think this is literally overcomplicating it, because I don't think like I think this could be over engineering it right now. I think it would be good to say command record so you're recording a command buffer and you're going to submit it, and you're going to record your commands and you'll submit it. Yeah, see, I don't know if we're going to do a work graph or like a frame graph or something like this. I don't know if we're going to do it for this project, but we want to have a way to start a command buffer, end it, and then submit it. So, see, I think Metal has like this thing called an encoder, and then I think they submit it back down by this thing called a command queue. I think they did it in their API. But for our API, we literally just want to say we're starting a frame. Say we're... and then probably submit a frame. Right? I don't know if we're having multiple command buffers. I really don't think we're going to be doing that. So let's just make something very specific. Frame submit. Right? And then you have your command. So let's try and roll with that. So here's the implementation of this. So what we want to do, go to submit here. I don't think we're going to have this buffer, command buffer thing anymore. Simplify. Love me a good simplify. Okay. This is awesome. So I think what we want to do is remove that backend.h. Maybe we keep it. Nah. I think we'll keep it. Backend.h. So that has all these things in. Yeah, just to clear. So this is implemented for each backend. So we've only got Vulkan right now, right? So there's some stuff that's shared between the backends, and then like validation and maybe setting stuff up, and then we funnel that into the backend to do specific jobs. So when you start a frame, there will be stuff that we'll do, but for now I think we're just going to call the backend. So it'd be backend frame start. And sometimes a function could call multiple backend functions. Like the interface doesn't have to be, is not always the same. It's just starting off as the same. They can all change. So then submit, command dispatch. Shader, num groups, BC size. So I think we might fetch something about it. We'll see. Wait, we're not doing that one yet. What am I doing? Get out of here with that. So let's bring these guys with us into the super lovely backend H. Chuck a load of voids everywhere because that's what you didn't see. And we're going to implement these guys now. So we're going to head into the Vulkan backend side of things. So when we start our frame, what do we need to do? So we need to wait for the previous frame to be done. So you're recording a command buffer. You need to be wait for these command buffers to be finished being used with. Make sure that the command buffers are not being used by the GPU. And if they're not, we can then start using them. And you also need to acquire your image as well. Did you consider removing high-level abstraction and just put in Vulkan code? Maybe when Vulkan code is ready. Right. See, the problem is Vulkan is like super manual and very crazy. And by putting it in its own file outside of like I think you're right in regards where I could just call directly into this, but then like the thing is so small anyway and easy to change that it's not so much of a pain. Um, like we only just need to, yeah, like I don't want to expose any Vulkan code outside of the Vulkan file, basically. Like, so I just want to like keep things abstracted and yeah, and just kept yeah. Like I don't want to create too many layers either. So by just having a function that just refers straight into the Vulkan code base is completely fine. So let's do what we always do apparently. Which is go to this example. So we create some fences here. Alright, so we want to, this is all some pipeline stuff, all some confusing stuff really. This is all pretty good, I think. Right, let's start here. So if the GGPU VK swap chain, if like the swap chain size, there are swap chain size here? Exactly, we do have that. What are you talking about? So the swap chain size dot width or height, if any of that is 0, we're just not going to do we're not going to do anything. Is that a good answer? No, this should be done outside. Because we might... Yeah, you should just not render to the swap chain image. Yeah, we'll remove that. That's fine. This is from the samples, where we get the sample data, but that's fine. Frame index. Sure, we need one of those. Now let's do all those find and replaces. What am I doing? Source, GPU. So we need a frame index. So this is just a number we're going to keep incrementing, and it will wrap around, and that's fine. Maybe we can use the U64. Is it fine if it wraps? What is the timeline semaphore? Timeline semaphore, because you can read back the semaphore value. 64. Nice. So we'll make it 64. I think we'll use this. Maybe. Right. So frame index with GPU active frame. See, should that be more of a... That's not really a VK specific thing. This is probably more of a internal thing. Right, so in frame start, we're back here now. So typically you wait for a fence here, but I want to try and use this timeline semaphore thing, because effectively in Vulkan, if you have two command buffers and you want to synchronize them, what you'll do is you'll get a semaphore and you say, hey, when this command buffer ends, signal this semaphore, and then for this command buffer to start, you say, hey, what semaphores am I waiting for to be signaled? And these are known as binary semaphores. But you can also use another thing called a timeline semaphore. And I want to give that a go. So we're going to do something a little bit experimental here. So effectively, a timeline semaphore is what you think a semaphore would actually be, where it's an integer that increments, but it doesn't actually get reduced or anything. It just increments for some reason. But anyway, so you instantiate them like so. So when you submit your command buffers, there's a lot of fluff in Vulkan, but when you wait, you can get it to signal. You get to signal to whatever value you want. Interesting. So you can make a signal, and then you can read it back CPU side, and then be like, oh, this thing is. And like the fence, it can be waited on directly for a wait value. Excellent. This is the way. Timeline semaphores the way. So in old Vulkan, you used to have to use a semaphore for GPU only, and then a fence to get. So semaphores used to be GPU to GPU, and then a fence used to be GPU to CPU communication to basically say, hey, this thing is done. But they've done this thing called a timeline semaphore now, where you can basically get it to do the job of what the fence used to do, and it's more transparent of what goes on. It's an actual integer, so it's pretty cool like that. So we're going to set up a timeline semaphore. So basically, we want to say, I think we're going to have one command buffer per frame. Now, obviously, in a proper game, you'll probably have more. But I think for this game, we could get away with maybe one per frame. We're going to give it a go. Right, so we want a VK semaphore. This will be our, let's call it semaphore, I guess, or so when it's finished, it signals that one, which means you need to have one per frame. So your command buffer semaphores, I guess. And you need one per. Yep. All right. So with the initialization here, we need to have this. So again, in true Vulkan fashion, you have some structures which link to other structures via the pnext field, right? Because they added the timeline stuff after. So initial value is 0, timeline type, that is here. Type create info. Oh my days. Designated initializers, yeah. Then we want create information. So these are the We need two of these, right? So for range, index 0 to GPU active frame count. How many active frames are we going to have? So device, which will be GPU VK device. Create information, and then GGPU. These will be the command buffer. Oh. VK command buffer semaphores. Awesome. Oh yeah, thank you for follow, appreciate it. Welcome, welcome. So we initialize those two there. So now we've got these semaphores, what do we do? So at the start of the frame, we want to do that wait thing. That is here. Oh, you can also signal it from the CPU as well. So it's CPU to GPU and GPU to CPU. Incredible. So you don't need to use events for that anymore. Anyway, so our wait value is a 1 maybe? No. I think we'll make it frame. Not sure yet. So we're waiting for... See, maybe the wait value is frame index take away 1 or something like this, or 2. No. I mean, we'll see. Let's have a think about it. So obviously on the first frame, it's going to be initialized to 0, so I guess that'll be fine. And we'll see how it goes. So we want to wait for one semaphore, which would be... Now we need the active frame index. So the active frame index is only going to be 0 or 1, because we've only got 2 active frames, but if we had 3, it'd be 0, 1, or 2, right? So we want to use one of those call GGPU VK device, wait info. Oh my days. So I typically like to stick, when you get this much code, I typically like to stick it in another block of itself just to section it as like, this code works together and anything after is not related to this code, right? Just section it off, it's very nice. So we're just going to quickly replace all of these guys. Oh no. Right, that looks pretty good. So this last one is like, how long do you want to wait? So we're just going to say wait as long as you need to. Wait forever. So on the first frame, this is going to be great. So I guess... Oh, wait a minute. I got an idea. So type create info dot initial value equal index. So then the first one is 0, the second one will be 1, right? And the next one will be 2. Yeah, that's good. Cool. So there's no need to reset anything here. Wait for 2 frames goes to be finished GPUs. GPUs will start doing stuff. Nice. Do you have a VR headset? No. Don't have a VR headset. I've used one before though. They're pretty cool, and you always forget how cool they are after a while. But yeah, I've played on them probably about 3 times. Image ready semaphore. I wonder if you can get a timeline semaphore with this. I don't know if you can. It might have to be a binary semaphore. So basically, like, what's really cool? Oh, we might have to split into two. Yeah. So what's really cool is like when you acquire. So this function requires the next image index for the swap chain image, and then you use that image index when it's ready. That meant it can block here, but when you're out of here, you can start recording command buffers. Now on the command buffer, like, it also gives you back a semaphore or a fence. So you typically want to have the first time you render to the display image, you want to have that in a separate command buffer that gets signaled by this semaphore, and obviously the semaphore and another semaphore for your command buffer before it. So that's, you're not waiting to render, like, because this semaphore will get signaled as soon as the image is ready to be rendered to. So you want to use the time on the GPU to do other stuff, like render to other images, and then when it's ready, you can actually get a signal, get your command buffer signal to actually fire off and start going. So the thing I'm looking for is like a Quinix image timeline semaphore. Does it have support for that? Oh, is it mentioned in here? Oh, it has to be a binary semaphore. One binary semaphore for present. What about a Quinix image? What do they use a fence for that? They don't even mentioned it. Yeah, guaranteed it has to be binary. If we read the spec here, it's gonna say, not gonna say timeline. Has to be binary. Uh-oh, that's fine. Right, so we need a swap chain image ready present semaphore. We get these ready. So I think I reset these because the semaphore might, yeah, it needs to be reset. Because I remember resizing it aggressively, and sometimes it'll be left in a state where the semaphore needs to be reset. Did they have a reset semaphore? They don't. Yeah, so we destroy it and recreate it. So let's re-enable this code. VK. Right, let's get these in there. Yeah, I played a bit of Half-Life Alyx actually. I played it. I went to a VR place in London, and me and my wife were playing it at the same time, which was quite cool. So she's not too into games, and it was the first time playing it, but it was pretty. We we didn't do too bad actually. We got quite. We had it like, she was struggling a bit to get through some bits, but luckily the guy that was helping her out play it, and get seeing where she was and helped her through it. Uh, and in the meantime, I was just playing with all the objects in the world and just throwing stuff around and shooting it. You know, it's pretty cool. I enjoyed it a lot. Um, there's only things left that needs the binary sum for. Yeah, and the present one, isn't it? Yeah. Yeah. The thing is, though, I remember aggressively resizing the window, and it destroyed the swap chain in a certain place, which left the semaphore unsignaled. Something like that. I forgot what it was. What was it? I have to think about it. Right. To investigate semaphore needing to destroyed. It does wait on it, doesn't it? No, that's not true. That's not true. You present this you present thank you for the follow. You present when you finish rendering, you signal the swap chain present is ready semaphore, and then the present waits for that to be signaled, and then it will unsignal it, right? For the next, it unsignals it. So the problem is sometimes it gets left in an unsignaled state I've had before. Needs to be reset. I think I remember experiencing this problem on Windows when aggressively or maybe Linux, I don't know. Right, that's what we'll investigate at some point. But for now, we'll just do the safe thing of actually making it work. Hey, Tolanese. Yeah, man, doing good, doing good. How are you doing? How are you doing? Right, so there's our semaphores. Let's go to the acquire next image. So we're gonna get our image index. Awesome. So, if we get an out of date or suboptimal, out of date means like you need to recreate the swap chain. Suboptimal means you don't have to, but it's best if you did. So you like we're just gonna do it. Any of those, anything else is an error. Yeah, this should really be inside of a function, hence I've just got so I can just return from here, but anyway. Yeah, me being lazy. So after this, what do we need to do after we record our swap chain image? So now we can actually start recording into our command buffer and everything, but before that, it's probably best if we set up our descriptor set, right? Set up our descriptors in the descriptor set. So what we really need to do this is very terrible code. All right. We don't have any resources other than the display resource, like the swap chain image resource, right, that we're displaying to. So what we want to do is like just simply, so remember the descriptor set, so I mentioned the array of descriptors. You need to update those. So we need to make sure we update to the right descriptor. I think it's gonna be 1, isn't it? How does one get the GPU? Where's the internals at? GPU internals. GPU surface resource index. So when we put that out via the GPU, it'd be that +1. So we get the surface resource ID, it's just that +1 because 0 is null. Let's close that as well. So in here, this one is going to be that constant we've just made, that surface resource index. So we're writing in slot 0. Oh, it is. Maybe we don't need to do +1. Let's put it as 1. Let's make 0 null, but we'll leave it as an empty descriptor anyway. We'll just waste a slot, I think. That's what we'll do. Yeah, so we're going to write to the index 0. This is storage buffer, this is wrong. We want storage image. If handled correctly, reset is not needed, in my honest opinion. Never had the issue against it. Right, yeah, I'm not... Yeah, I only did it like that. I thought that too, but I only did it like that because I actually experienced a problem with it by aggressively resizing it to have a bit of it. So maybe try aggressively resizing your Vulkan app and see if it does it, because it happened on mine. So we'll have a bit of a play. So buffer info. So we need to write to a descriptor. Well, sorry, it's an image, isn't it? So the image that we're writing, so we'll say like to do, write all the resources to the descriptor set. So the HCC interrupt code helps us write this out, but as well, which is kind of nice, I guess. But it helps out a little bit. It helps fill out one medium-sized structure. So we get our image here. Typically what you want to do is fill a massive array of these and a massive array of these a massive array of these, and then upload them all in one go. But yeah, that's fine. So basically this thing that you fill in has like what descriptor set, what binding in the descriptor set, where's the destination array element, how big is that, and what is the type of it. So is that type a storage image or storage buffer? And then you have your pointer to the image descriptors, right? And it's an array of that many. So bear in mind you can fill a whole array of descriptors really like with just one call. But yeah. Oh, did I close it again? Sad times. GPU Vulkan. Right. So it's actually an image info, VK device. This is super lazy. We should batch the descriptor writes into a single call. Hey Drots. No, I'm actually not using the Corsair. Taking a bit of a break from it. Just to get a bit of a different experience. Because I've been using it for a while now, so I just want to. Yeah, I've gone back to my older keyboard, my Mac 2007 keyboard, like the flat one. It's horrible, and it's absolute crime against all programmers out there. But this is what I'm rolling with for now. It's just easier to type on, like less finger movement. But yeah, I'll go back to the Corsair when I'm gonna get bored. Logitech K120. Logitech K120, eh? Let's have a gander. It's pretty basic. I really like it. It's very small key movements. Like if you have problems with your hands on RSI, like you can, it's really soft and you can sort of like just glide your hands over and just very small finger movement, and it's a lot easier on the fingers. Like with these mechanical keyboards, they feel really nice to type on and they're already cool. But if you type on them like for 12 hours a day, 5 days a week or whatever, it does make my hands a bit like really tired and like of and joints hurting a bit sometimes. But that's after a long time using it. So it just depends on your and like your body really and the anatomy of your body, right? Yeah, this one looks pretty standard actually. I remember seeing this one. Fair play. It's got a small enter key though. Oh yeah, I like this one. The classic UK enter key. Big fat thing you can just press, you know. Oh, your fingertips hurt. Yeah, for me it's more of this pinky and that one sometimes. Of those control keys. Hence why I use Vim. Right. Yeah, it's the bee's knees. It's what you want. Oh. Right, so that's going to update the descriptor. Right, so now we update the descriptor, we can finally record the command buffer. So we can record the command buffer, we can put some commands in there, end it, then submit it. That's what we're going to be doing. I'm just going to take a quick break and get another drink. But I'll be back in a couple of minutes. So enjoy the tunes while we're gone. Alright, welcome back everybody. If your fingers hurt on the mechanical keyboard, you should switch to linear keys, helps a lot. No switches. Yeah, the thing is, I don't think I've got changeable switches in my keyboard, which sucks. But yeah, I'll keep that in mind. Is that like a, because I've got the red cherries, is it like a brown one or a blue one? Is that right? Right, so now we can actually start recording our command buffer. So again, I've already written out the code, saves us typing out, and we can just talk about it instead instead of typing out, right? So you can, is it a reset you need to do? Yeah, get the command buffer, reset the command buffer, then begin it. Then we'll get this push constants thing as well. Talk about that in a sec. Oh no, we won't. Not that push constants. Get out of there with it. No, please. That's too soon. So you want to do the good old GGPU. VK command buffers with the active frame. So we get the current one for the active frame, the one that we've been waiting for, right? The one that we waited on. And then we reset. See, actually, a good idea would be update this first. Wait a minute, will it? No, because you're waiting for it to be finished. Excuse me. Yeah, it's correct, isn't it? You're waiting for it to be finished. Then you acquire. Yeah. So GGPU. So you need to do this thing to say you're going to submit it one time. Actually, maybe transient isn't what I was thinking it was. Right, one time submit. Reset. Sweet. So now we're actually recording the command buffer. The command buffer is in the recording state. And we have to reset it because, so you get into a recording state, then you get it into, when you end it, it goes to a recorded state. And then you can reset it there, or you can send it to the GPU and it can use it. And it's still in a recorded state, I think, after that. But yeah, you basically have to, you can't begin it, you have to either reset it or free it. So now I've begun the command buffer for recording. The next thing to do would be we need to bind the descriptor set. GPU. That's really interesting. Why did the... Right. GPU. HCC interrupt. So we need that pipeline layout thing as well when we bind these descriptor sets. We only need one descriptor set. Like, again, descriptor sets are a very complicated thing, but we've simplified it to make it a very easy problem. So we're essentially just setting descriptor set 0 and setting one of them, because you can actually set multiple of them. And we're setting the one for this frame. Yeah, that's basically it. It's very complicated thing to explain the whole way, but we explained a very high level idea of what they were earlier. I wonder why I didn't do it that way. Right. So now we've bound it to the command buffer. You need to bind it to every command buffer, I think. It needs to have it in binding. I think it gets reset ends when the command buffer ends. What else do we need? Let's take this end command buffer with us. So I'm pretty sure we only need to... Oh, come on. There we go. So after we've bound our command buffer... Sorry, bound our descriptor sets, start recording the command buffer. I think we can just start doing dispatches here. That should be fine. Well, distro, this is Manjaro Linux. Red switches are usually linear. Oh, okay. Yeah. That's good to know then. You use red switches. I don't know, I've been using red switches. I've just been... Yeah. Oh, so VK. Let's get the VK result here because we kind of use a macro that depends on that. In there. Right, so if frame start then frame submit, so you need to end the command buffer. Now we need to, should we fill in the dispatch? Let's fill in the dispatch as well. Before we do the submit, just to sort of put the icing on the cake of what we're doing with this command buffer. So in between frame start and frame submit, what we're going to be doing is we're going to be calling... well, we haven't got it here anymore. Right, so GPU frame start, GPU frame submit. Then we're going to be calling GPU command dispatch, like so, with our shader with the dispatching, right? So in here, I want to add the dispatch. Now, what do we need access to exactly? We haven't done any pipelines yet. We haven't created based on our shaders. Okay, this is fine. Yeah, I think it's just basically the same. We pass in everything again. Shader, num groups, BC size. I think that'll be fine. Again, I'm hoping to be able to not have just a very simple thing like that, but maybe it is going to be like that. So I'm hoping to have a back-end implementation for this. So the dispatch, what do we need to do here? So we need to record a command into the command buffer, which is going to be... We need to bind some form of pipeline. We also need to bind a... We also need to upload the push constants, which is bundle constants in this case. So HCC interop. VK shader stage compute bit, because we're only setting the push constants for the compute shaders. Where's the met? Oh, the metadata is included, isn't it? Yeah. Cool. So we don't have a single pipeline yet. So we haven't actually compiled our shaders. So HCC produces this metadata with every compilation. And then, so I would like this to have a JSON version in the future as well, so we can reload, and then get this at runtime. So yeah, so we can reload our shaders at runtime, which would be a really neat feature. But anyway, it gives us metadata, it gives us the name of the shader we got, and other things. It's all very work in progress, this, but it's good enough. Why do we care about this? Because it gives us the name of each of these, so we can go over all these shader infos and compile our compute pipelines. So, and we can map them to it. So basically, what we want to have is all of our VK pipelines. So pipelines are actually a real big problem for big game engines and things like this, because they have tons of shaders. We're just going to try and make it a very simple problem, and if things get more complicated, we can solve it there, but I don't think they will. So what are we trying to do? So basically we want to have, oh, why isn't there a count there? You have foiled my plan. Right. I guess we've got to edit the HCC source code. What do you reckon? I reckon we can have the count thing here. I can edit the source code so we can get that to work. So we want to go over all the shaders, and we want to compile all those pipelines. So effectively, we want to be able to say, find the pipeline. So it'll be GGPUVK. Pipelines, index it with the shader enumeration, right? And we'll just bind that one there. Then the dispatch group size. See, num group's terrible name. Nah, num groups is fine. Screw it. .x, .y, .z. Perfect. So we're recording 3 commands in there. Push constants, we're going to bind a pipeline, no one dispatch. Now, it's better if you don't have to keep rebinding stuff. If it's already bound, obviously it's already bound. So really what we should be doing is we should have like a VK pipeline bound pipeline thing. And we say, hey, if the pipeline is not, so we get the pipeline, and that's equal to this thing. And what I want to say is, if VK pipeline is not equal to the GGPU VK bound VK pipeline, then we can record this in there. If not, there's just no point in recording it because it's already been bound. And we just got to make sure that this thing is cleared to null at the start of the frame. Something like that, yeah. So that's pretty good. So that is what it takes to actually dispatch something. Now the issue is, we can't simply do tons of dispatches and say dispatch, 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 because you'll have synchronization problems. And synchronization is one of those big, well, it requires a lot of, kind of a big engineering effort. But again, I think we're going to try and roll a hand-rolled simple solution just to get going. And if we need to do anything a bit more complicated, we can solve that. It's connected to the table, the microphone. Hey Silvercore, how you doing? Good to see you. Yeah. Guess who's making a game about an engine? Yeah. Damn straight. Also back to using same C++ subset. After non-stop months of C/Odin. Been clean so far. Yeah, exactly. When you see, you'll see. How dare you leave the C's? uh, yeah. Yeah, it's difficult to figure out how to solve it. How to solve that problem. Maybe I need to attach it to the get an inmax down, attach it to the wall. Probably be a better idea, wouldn't it? Janza, we're never going to draw triangles. What are you talking about? We're never going to draw triangles. We're only going to use compute for this game. We're doing something untraditional. Okay, fair play, fair play. Is that a link I can click and get viruses on my machine? Oh no, it's infected my computer with a white screen. I can't see it. I cannot see your C. Rightio. So we need to instantiate these pipelines. So how does one instantiate the pipelines? So in Vulkan, graphics pipelines are complicated but compute are just dead simple, hence why we've just referred to it via an enumeration. So when we create our instance, we want to go over all of the super lovely, we'll call it a shader. 0 to HCC shader count. Wait, what's the interrupt look like? Yeah, that'll be it. So you want to say, right? I've got to go and find this now. VK. Wait a minute, I've already got it in the other one. Compute pipeline. Oh yeah, this is what I want. So I think we don't want to recreate the object every time. Instantiate this thing once, please. So the shader module, we made the shader module yet, have we? So again, let's get this one out. We haven't read the file yet, have? Oh, we haven't done a read all file. Oh my days. So shader module represents a SPIR-V binary. We need to get that from disk. We should be able to do it pretty quick. Let's go into HCC, samples app, operating system Linux, isn't it? Platform Linux, that's what I want. Right, let's read all these buggers. So in the game, it's OS Linux. We want to have a simple one that just reads in a whole file because that's all we need right now. It's gonna malloc. Oh, it's gonna malloc. Makes me cringe when I malloc. Right, so include standard lib. So we'll implement that in the OS interface. Sorry, we'll put it in the OS interface as well. There you go. So we've got this now, we can just use that. It's just going to do an fopen read all. So if people are not familiar with it, just quickly glance over the code. Effectively, it opens up a file in read mode. If it's not there, yeah, returns false. It does the terrible old school way of seeking to the end of the file using ftel to get the file size and seeking back to the beginning. Then it allocates some memory, reads everything into that memory allocation. If it failed, it returns false and then sets the data, then closes the file, then it returns true. So it's very, very simple. Typically, I would prefer to use the operating system directly, but I was just being lazy there. Hey, x86 me, thank you so much. Oh yeah. Thank you for the sub there. Appreciate it, sir. Namespaces, Windows subsystem. C methods. This is not C. Oh, cool. You got like a fun key to action. Right. I see. So you like using strings for actions? Is it because your actions are sort of like cross, or do you not know the actions ahead of time, so you can't put them in an enum, for instance? Is that way? Righty, oh. Right, so you should be able to OS read in all of the things. Now the this shader path, I don't think we've defined it anywhere. So I think we can just say, we can just put this in the GPU internal header. Shader path, where's that? It's in build. Well, no, it's not in build because it'll be in build. Anyway, build slash. I'm looking. Shaders.spirv, of course. Of course. Right, so now we've got this thing in there. So I'll read in all the code, the spirv code that we compile with our custom compiler. If not, it's gonna complain and then, yeah. Wait, that's the wrong one. This is the right one. If not, it's gonna complain. This is a GPU. This one down here is a GPU. It's a big old replace of that. Oh yeah. So we create this thing called a shader module. A shader module again, just sort of wraps. It just loads in the spirv binary. It does some checks, does some bits and bobs, bells and whistles. You know, it doesn't compile anything from what I know, but maybe it could compile some stuff. I guess it's up to the implementation. I'm not sure. So now the GPU pipeline, compute pipeline, this, like, whenever you create a pipeline, that's when it compiles the shader. So you need your pipeline layout. So this one's actually really simple. So what we're going to do is we're going to say create information for this guy. is going to be the stage dot p name, which is the entry point name, is going to be equal to the shader infos array that we saw in here. Right, shader infos, we use the enum, get the name, and this is all generated by the HCC compiler. So we can just pass in the shader enumeration and then get the name. Then we're going to compile each of these lovelies. GPU vk pipelines shader. So it's just going to go into there. Now, again, shader count is not declared because the shader compiler doesn't do a final enum there. Complete rookie mistake that is. So we're just going to correct that. So I'm going to go into the HCC code base. Like I said, I wouldn't never do, but anyway, I'm going to do it now. So we need to go into like the metadata generation side of things. Basically, there's a function where it will start, generate for a C header file. Here you go. So here's the enum. Right, it goes over all of the shaders and does some magic. So we just want to simply do the one at the end, where it does the count. So it's going to say this underscore count. There's a prefix. There you go. So that's all we need to simply put in. It's going to output that now in the final count one, which would be super handy. But I've got to go ahead and recompile my compiler and then bring it over. So just going to go over to here into HCC. We're going to run the super lovely build script, build a release package, and then we're going to go and get that when it's finished. It's done a good job apparently. All the tests are checking out okay. So we're going to go into what we're doing. We're going into game without an engine, third party, HCC. We'll drop in the new binary because I need a binary changed, right? Nothing else changed, only the binary. So now if we run it with a new binary. Oh, it's underscore count. Ah, ruined. Right, that was a big epic fail. So we'll go back there again, remove the underscore, and we'll go back into HCC, rebuild the release package, and then we're going to do the same dance again, where we go into HCC, get the latest release, grab the binary, throw it into the thing. I should probably make a script for that just to, well, I don't know, it's not too, we probably shouldn't do it too often. Fingers crossed. So press the F5s and it all compiles. So, right, what does this mean we've done? It means now we have pipelines, we have a command buffer that gets recorded, and we have so we create our pipelines, we record command buffers, we put a command buffer, we do a dispatch, and we end it, but we don't do anything with it. So how do you submit this thing to the GPU? That is the question. What is your color, Bugatti? It's just a custom theme I made. It's more of a red orientated one because I had a blue orientated one before. OpenGL is not bad for 2D, but 3D stuff tends to get a bit messy. Yeah, I think all graphics APIs are a bit messy in general, isn't it? It's dumb simple, each action name is chart U32, right. That mem compare in a loop and find the action for requested, right. Should do for now. Ought to be good enough. Am I planning to do some sort of software ray tracing and compute, some sort of raycasting? So I don't really want to reveal too much on what I'm doing. I'm saving that for when we get there. Purely because it's kind of a unique idea in terms of like what people are currently doing with graphics. So I don't want to. I want to reveal it as and when I'm doing it. Hate doing the whole D3D compile process blobs in this. Call D3D blah blah blah. Check it with compiles. Right. But don't you just put that in a build script, right? I don't see the issue. Hey there, Kappa. Yeah, I don't drive a Bugatti. Where is the queue exactly? Splatting? Maybe. Maybe not. Vulkan makes GPU program more like CPU programming. Not really. I'm not sure what you mean by that. Like, but yeah, we tried to make the HC compiler tries to make the HC compiler itself tries to make GPU programming, well, like CPU programming in a way where you can use the same language, but still, that you've got to know the hardware underneath, which is different. Right. So let's get submitting. Right. Let's do this, and hopefully we get it working today. We'll see. So, right, we need all this stuff. This is timeline semaphores. Bruno, we need to do a present as well. So much rocket science in all of this. Oh, we didn't wait for the signal. Oh no, sorry, wait for it here, don't we? There. Alright. Also, I remember there was a const somewhere. Who writes const? Oh, these const people. Right. So there's like a signal. Right. Okay, interesting. So what are we trying to do? So we're trying to submit. You got to submit your command buffer down. Yeah. So you're submitting your command buffer, and it needs to wait for a certain semaphore. So it kind of needs to wait for a signal value of whatever the previous frame is. So your signal value to start is probably going to be whatever GPU frame index is, right? So that's for the time. So it starts like whenever it reaches that. Then when it's finished, it becomes that plus one, right? So then it'll trigger the next frame's one, right? Binary unblock. Oh wait, signal semaphores. Oh, where's the signal values? Oh, signal values. Oops. Plus one. Got that wrong. Right. Signal values. So you have this timeline semaphore. Submit info. So you wait. Where's a wait value? So what are we waiting on? We're waiting for two things. So we need to wait for just get rid of that. Just read the code. So we're waiting for the previous frame and waiting for another binary, which should be the present ready. Bear in mind the present ready doesn't have to be, like, it should really be done later, but again, this is the first version, so we can make it better later. So what are the signal semaphores? The signal semaphores are and we need wait semaphores as well. So wait semaphores, signal semaphores. So before we fire the command buffer, we need to wait for GGPU VK command buffer semaphores. Now you got this active frame index. You need like a previous active frame index, which will be a -1. Right? Now you're waiting for the previous frames semaphore, and then you're also waiting for this not present ready, swap chain image ready. Right, this one gets signaled when they acquire. So you do that VK acquire next swap chain image. That will signal the semaphore when the image is ready to be rendered to. Now, I want to write to do here to say, really this should be like, we should split the command buffers so that the first write to the swap chain image is at the start of a command buffer. That we can signal with this semaphore and do other work while waiting for the swap chain image to be ready. Perfect. So for now, let's roll with that. Signal semaphores. You can signal the next. You're going to signal the next frames semaphore, which could be the same as the previous. It is the same as the previous in this instance. And then when you're finished, you're going to signal the present ready semaphore, right? So hopefully that all makes sense. Maybe a signal after present, we'll see. We'll do. Yeah. It's a big like, it's a lot of rocket science, all this semaphore stuff. It's so silly. There's lots of ways to express it. And just the way you have to daisy chain command buffers together as well. It's like, why couldn't you just have, like, they say, like, you have a command buffer, and when you submit another command buffer, it's as if the commands are going execute. Like, they say this all the time, where like, as if the commands are in a linear array. But it's like, why can't we just have one big command buffer, and we simply like have this waiting and signaling, like in the single command, but you know what I mean? It's like, why couldn't they just do that? Like, why do they have to split the command buffers? It's just silly. I'm to split these command buffers all the time. In director, so I'll wait for the other frame fence value, then set this frame to 1 plus the other frame. Right. Yeah, I'll have to think about it. Yeah, this is probably going to be wrong or not scale well. But yeah, we're just going to try and get something working. But yeah, thanks. I'll keep that in mind. So you set the other one. Yeah. Yeah, because the fence in DX12 is like a semaphore in Vulkan. Is anyone asking how much did you pay for that vehicle? What vehicle? Didn't have a Bugatti. Will I be dividing meshes into clusters meshlets like Nanite does? You have to wait and see. I'm not spilling the beans, but I have said I'm not working on triangles as a base. I'm not rendering triangles. I've said that before. Um, so what are we doing when we submit, right? So you got the wait semaphores. Wait semaphores. We've got 2 of those guys. Right, so I got this array count thing. Let's use it. Array count. It just does the size of and divide by size of. Like, pretty nice. Then we've got the signal semaphores. Alright. So, include the command buffer. What are you talking about? Right. So, what are we doing? So there's command buffers right here. Excellent, that's what I want. Right. Gimme. So the count is going to be 1, and the command buffer is the address of VK command buffer. So the only one that we've recorded, right? So we need a queue. ggpu dot vkq. Then we put in our submit info. Okay. And there's an optional fence you can get signaled when it's finished on the GPU. But we don't need that. Yeah. Yeah, that's very true. Like sub passes and everything. Yeah. Yeah. Yeah, it makes me think sometimes, like, why didn't you have 2 different APIs? Because it is really crazy. Um, so, right, this doesn't present though. So this will queue a submit. Now, we still have to do the present. Oh, wait, what about this present mode? Wait, what do we do as present mode? FIFO. Don't use FIFO for a game, but it's only what's in there. Right, to do. We gotta look. We gotta do our. We're gonna spend time doing our to dos, all of them. We're gonna do it one stream. When we got the basic graphics thing all set up and working, we are gonna do it. So submit, after a submit, we need to do a present, like queue present. So you need to queue a present with the queue present info. Wait, I've got this in the other one. Gotcha. All of this. This is what we need. Then we need to wrap this in a GPU VK assert because it returns a result. Want to keep a look at that. So we get the present info. Let's do this find and replace here. So we're gonna fire, right? The present is gonna wait. Like the present needs to go. Ugh. Maybe that's the wrong way of saying it. The present is only gonna happen if that semaphore present ready has been signaled from the command buffer that does the work on the GPU, right? And we pass in. Oh, that swap chain image needs to go GPU into this global thing. Right, we'll get that in there. Just give that a quick little rename. Yeah, so we're basically saying we are presenting the swap chain image for this frame. So when that's done, we're going to put it on the present queue. Then we get a result back. If the swap chain is out of date or suboptimal, you kind of need to, like this, I don't know if it's good to do it here. I think it's good to mark, like, I think it's good to destroy it. Yeah, I think it's good to destroy the swap chain here. And then later on, yeah, I need some sleep too. It's getting quite late, but yeah, I want to get this compiled and see if it works. Yeah, I know, right? It's easy to not do those 100 to-dos, isn't it? Wait, what is this? Improve Vulkan swap 2 chain deep. First in, first out vsync. Acquire using the semaphore. Break the single submit. The whole frame waiting on that semaphore with no signal. I'll have to process this later. I'm very tired and this seems very... Like, TLDR, what is this? What's the benefits? Yeah, I'll read this in a bit. So if it breaks here, you could recreate it, but maybe it's best to just recreate it when you acquire. Yeah, Buzzword Blue, do it. Right, to do, we want to fix this up in a bit, but yeah, like, we want to like, you know, like, we want to like set a global, you know, take note, maybe like destroy swap chain here. We want to already destroy it here, actually. We can't do that. No, yeah, we just want to take note and then that it needs to be reset. But then also we don't really care about that. because it's just going to go in here anyway. Like it'll try and acquire it, then it'll be error or out of date anyway. Yeah, I think that'd be fine. Okay. So, this should be it. This should clear the screen to red, but probably not going to. So it compiles. Let's see what happens. Timeline semaphore. Feature is not enabled. We need to enable the timeline semaphore feature in some place. No worries. Vulkan 1.2 features. So we're going to look for those. So we use timeline semaphore, so drop these in. Then the next thing that fails is the compute create. Expects at least 1024, but only 256. Right. Basically, in the shaders I compiled it to 1024, but I've set it as 256 for the descriptor arrays. So we'll just change it here, it doesn't matter. Wait, it's supposed to do there. Do we need this many? Well, what's this one? So, null descriptor feature not enabled. Must not be a null handle. But why is it a null handle? Because we would have acquired the image by now, right? Ah, swap chain and friends isn't being called. It's not good. It must be called. What is going on? It's just, he also mentions compute-based graphics, but that's something to worry about for now. Right. He said presenting without using weight semaphore. Hmm. So this should be called, like, start frame 15. But you've called initialize, right? Because we've seen it happen. Oh, does it return false? Oh, ooh. Chorus, like, yeah, so if you can have created, it would have returned false. But that doesn't matter. So if the swap chain doesn't exist, like, no, I'm just gonna put breakpoint in. My brain cannot work this out, right? Core breakpoint. GF. Right, hit the breakpoint. Just have a gander. So it does stuff. Where we like stuff. Sets this whole thing. Creates the swap chain. Oh, no images. Would you look at that? So it doesn't set that number. Right, which means that. So basically, what it doesn't do here is I used to call it with null, and that would set count. That says count to the value. It's just typical Vulkan. If you have a count and then a pointer at the end of values, and you're fetching an array of things back out. If you pass in a null at the end, it will set the count with the value that you want. Then if you don't have a null here, the mode is I'm going to populate the array. So it uses this count as the array, the size of the array. So you actually want to call it and get the count first. So let's try that. Cool. Next problem is on the dispatch. Statically uses index 0, which is not compatible with... Oh, because I've got an upload buffer. Is it upload? Sorry, I've got a print buffer. It's got a print buffer in there, so I need to quickly... So in HCC we actually have printf support, and we can print from shaders, and we print back into a buffer, but we haven't set that up at all. So basically what we want to do is write to do actually set up the printf buffer properly. So right now we don't have a print buffer, so we're just going to do 0. Did I have a way to custom set that? Yeah, we're going to investigate that. This is good that we're doing this because it means I can see the problem. So you might want to have the print buffer be a different number. The script's index 0, which is not bound. Oh no, maybe it's not the... Create with pipeline layout statically uses used by pipeline bound. Right, let's read this properly. Is there 9% the change, or you did is throw away because you want to change the... Yeah, that's a very common thing. So maybe the way that we're doing it here is a good reason. Another good point for that reason is because as a solo dev, you probably get better, so you typically want to rewrite it anyway. Yeah. Hmm. Yeah, you could make some like creative application for artists. Like it doesn't have to be a game. You know, you could make something that helps out production in movies, you know. There's all sorts you can do. Just gotta think and start doing it. Right, what's this error? So statically uses descriptor set 0, yeah, which is not compatible with the bound descriptor pipe. What? Not compatible? Oh no. Wait, I'm confused. No, I'm really confused now. So this pipeline created with this pipeline layout statically is a descriptor set, which is not bound to the descriptor set's pipeline layout of 0. Why has it got a null pipeline layout? Why was it allowed to be created with that? Like, oh, bind point graphics? Huh. That's probably why the bind point wasn't right. Right, that changed it. Yes. So the bind point was wrong. It was binding it to the graphics side, so the descriptor wasn't bound. Rookie mistake. So I guess this isn't it. This is fine, I can remove that. Yes, right. So wait semaphore count is 0. So let's look at that submit info. What are you even saying? If wait count is not 0, must be a valid pointer, a valid putter. Is a valid putter. To an array of counts with combinations of message values. Oh, we didn't use weight masks. Do we overwrite those? Where's the example? The timeline semaphores. It skipped on the weight mask, didn't it? I'd like to think it did. Right. We'll just do end of. Alright. Destination masks. Stage masks. So what was a stage mask? Basically, you tell it to wait after it's done. What's a good way of explaining this? Wait DST. Right. So a stage flag is basically like this big thing here. Now, typically, like you have different like stages, like vertex shader, fragment shader, you know. But so this is, but like we don't need to use like a lot of this stuff. But yeah, like the stuff like top of pipe, bottom of pipe. Effectively, like think of it going down from top of pipe to bottom of pipe, and it goes through it in this order of vertex shader, tessellation control, geometry, fragment test, early fragment tests, and that. But then it's only you can only think about it for the traditional triangle rendering pipeline in this sense. But things like compute shader, transfer, and this are kind of separate, but they're bundled it in the same. Like it's a separate idea. But yeah, typically you refer to like this semaphore here is waiting at the end of the command buffer. What is the last thing at the end of the command buffer that it's waiting for? Well, it's waiting for the compute shader stuff to be finished. I don't think we have anything else. The only things we can have is transfer, maybe. So I think I can just say compute shader bit. But if you don't know what you're doing, you can just say bottom of pipe, basically, or all commands. Yeah, we'll be touching more on this pipeline state in the future when it comes to actually doing synchronization code, because right now if we do multiple compute, it's just gonna, everything's gonna overwrite each other, and it's gonna be fireworks on the screen. So for now, we want to avoid the fireworks. So I've only got one of these guys. Wait, is it two? I don't know, we'll see. Yeah, it doesn't want two, it wants one. So Pipeline Shader Flags 2 is the second version which has more options, and it's pretty good actually. It's under the Synchronization 2. It used to be an extension, but now it's part of core. But anyway, we'll explain that later. Right, so let's try that out and see how well we do. Crashes again. Wait semaphore count different than the... Oh no. Core array count. Oh my days. Weight values. I'm so glad that the layers are catching problems like this. Timeline. Oh no, it's not changing all that. Let's just use these. I prefer these, they're way better. Oh. Right, let's give that a go. I think there was a copy and paste there. I don't think I typed graphics out of habit. I think it was copy paste. Yeah, I copied it from the HTC samples application. Oh no. So it must be greater than the current value 1. Ooh. We didn't increment frame index. But I doubt that's the problem, because I think we render a... I don't think we rendered a frame. Let's run it again. Right, so it's saying that signal semaphore's value must be greater than the current timeline semaphore value of 1. Signal to the next... Oh, okay. So we initialize those timeline semaphores we actually changed. We initialize the timeline semaphores when we create the GPU backend. We update this initial value, but I think I want to set it... Keep them both 0. Because it's talking about it's signaling the next semaphore. Value. Maybe you can use the same semaphore, I'm not sure about that. Excellent. Right. So now we need a transition barrier to transition the image into present source KHR. So this is part of the synchronization code that I was talking about, which I'll refer to. But we're going to go over to the sample code in HTC and just get that going. So it's basically one of these guys. Like, we're going to automate this. Are we? Well, this might have to stay in here, I'm not sure. So where's the command buffer end? Right, so frame start, frame end, let's submit. So before we end the command buffer, what we want to do is actually put one more thing in there, and it's a pipeline barrier. So what pipeline barrier does is it says, hey, wait here until everything above, all the commands above me, up until the previous pipeline barrier, have reached this certain pipeline stage, or finished this pipeline stage. And what is it doing before, and what is it doing after? That's basically what it's saying. And what's happening on the other side of the pipeline barrier. So you typically have these waiting, is to wait, but also it can do layout transitions. And basically, I'm pretty sure what image layout is it changes the way the pixels are laid out. Like basically from one tiling format to maybe another one, or to a linear format or something. But again, not quite sure. Like it is what I assume after using Vulkan for a period of time. But I've not seen it. I don't know. I've never seen anything under the hood, basically. Because you essentially, yeah. Right. So we're translating it from general layout. So this comes from a shader, which will typically be laid out in. The way I think about it is because in shaders you would let the pixels will be laid out in like tiles, so you can read them effectively in the shaders and be cached effectively. But when you present it, it'll be in a different layout, right on the screen. It's not gonna be tiled anymore; it'll be linear. And there's another one for like, yeah, there's other ones. But anyway, so what do we need to do here? We need to get the swap chain image. So we get the current swap chain image, and we're going to transition it. So we're saying, hey, everything above this pipeline barrier, well, we're saying this image is used in a compute shader, and it's the way it was accessed is via storage. It was a storage write, so it was like a storage image, and we're writing to it. Then afterwards, it's not going to get used. Could I say present? No, it doesn't say. So you say none. It's just not going to get used after this. But what we're going to do is we're going to transition it from a different layout, from a general layout, because that's what it needs to be when you write from it in a shader. It's in this general layout, and then you transition it into the new layout, which is the present source image layout. There's some sub-resource tracking stuff, but there's no sub-resources here, right? It's just one array layer, one MIP level. Then, right, what else? GPU. So this is the actual dependency information for the pipeline barrier. The core, rather. So typically, for this pipeline barrier 2, which is the synchronization 2 stuff, you'll basically fill up an array of image barriers like this, an array of memory barriers or buffer barriers, which are very similar. And then you'll call this thing here. And remember, it says everything before me is like these source masks and that. Like, how is this image used before? And how is it used after? And then it will wait for the before, and then it will sort of prepare for the after. So this is how you do synchronization in Vulkan. It's a little bit crazy to get your head around, but yeah, when you write some code, it's not so bad. But the issue is like to automate this, it's kind of a big system. So we're going to try and maybe provide functions to make the specifying this manually a lot easier. And it will be a lot more simple since we're only using compute shaders. So it's essentially just going to be, I don't think there's going to be any layout transitions, mostly access, waiting on read. You know, I've written to this resource and then I'm reading from it after this barrier, so we need to wait here. So stuff like that. So that's going to wait, and so it's not going to end the command buffer until that is done. So let's see how well this performs. Queue submit command buffers, image, sub-resource, aspect mask, whatever, must be in general, instead the current layout is undefined. What are you referring to? Look into that. Do different hardware and NVIDIA use the same swizzle patterns? I think it may be tiled heavily to allow the driver to handle. Tiled heavily to the driver. Yeah. I don't. Yeah. From what I've read and what I understand is each driver, like, okay. So the Vulkan doesn't expose anything specifically. So each driver has the free will to do whatever they want. I've heard on some mobile platforms, like, they don't do 3D caching. They don't have like a 3D tiled layout for 3D textures. So yeah, it's it all varies depending on the platform, which means then obviously all of the different if you have like the different functions in the shaders that read from textures will perform differently. Also depending on what layout they're in as well, because there is a read-only optimal and there's a general layout as well. So it's in layout undefined. Like, what? Like, we only have one image, which is the surface, right? And we're simply, so it's saying in the submit. Oh, wait a minute. Wait a minute, you plonker. Wait a minute. We need to transition our swap chain image to be in a general layout. For the compute shader, it's about to go and put some pixels in, isn't it? So we're going to throw that in there. Swap chain image, please. What we need to do is say, hey, previous thing is none. The next thing, yeah, previous thing is none. We want to be able to write from it in the compute shader. We're going to transition it into a general layout from an undefined layout, meaning we don't care what it's in. Oh yeah, welcome. What else we're going to do? Yeah, so we're going to fire that off. Transition. Yeah. So much code, right? Vulkan TM. Oh my god! Oh my days! Could you believe we were going to do this today? Could you believe we we're going to do this today? It's running, isn't it? All right, we're broken now. Can we see what's going on? Print rendering frame blah ggpu frame index. Come on. U64, you say? ZE, my friend. Oh no, when it is 0 then 1 and then it stalls. What a pain in the butt. I don't know. It's not the same from what I understand. It's different layout. I do not know though. I have no idea. It's definitely a different enum. So it's up to the driver, I imagine. So why does it stall, eh? So obviously, like, then the next frame one, like, it's obviously waiting. So, alright. So, signal that, right? And then we're waiting. Wait for. Oh. Wait for 0, signal 1. Wait for 1, signal 2. So, why do we see no wait for? So if I hop into the debugger, do a control C, do a B, say break. Why are you stalling there like a bugger? Timeline wait. Is it because we've huh. Why is that? VKQ present stall. Blocking. Exactly. Um Maybe we can put some prints around it. But could it be that we're presented like maybe the stuff on the GPU could still be running for some reason? Like is the signaling not the signaling not happening right? Also, can you signal the same semaphore that you've been waiting for? Do we only need one semaphore? Like why do I keep why do I have two semaphores? I think this is silly. Should we try and change this? Alright. Did they implement DX12 for macOS? Yeah, I know they did that translation thing for the shaders. Wait, when did they implement DX12? What's this for? Is it like a translation layer? Homebrew Apple added DX12 supports macOS and Silicon via its game porting toolkit. Basically 20k patch to Wine. Huh. Are they doing that because Valve has done it and it's proving success, and they want people to use their M1 hardware for gaming and get the gaming crowd over? Is that why? Yeah, I think I heard something like this. Someone told me that at work, I think, today. I heard that today from someone. Sounds bloody weird though, doesn't it? Right, let's try a single timeline semaphore and see what happens. See how much this blows up the computer. Does it work? Initial value 0. That's what we like. Address the U, please, my friend. So wait for this guy. Signal the same guy. I'm hoping this works. Yes, this is when it at the start of the frame. So we had the previous index, then we had the next, and I don't think we need those anymore. Alright. So let's see if this buggers anything up. Oh, and it works. Look at that, we fixed it. Oh yeah. Excellent. And we can resize, and look at that janky. Look at this lovely noise. Oh my days, sorry if people are not liking that, but I like this version. Stick as my background. Anyway, because we're only running 800 by 600, you see, and then you get some random tiling stuff going on with uninitialized memory. But yeah, it's cool. Right, so we completed it. Apple be like, you got a graphics API, no problem. We'll support it as long as not Kronos. Yeah, I have no idea why. Maybe because they're annoyed that Mon VK exists, isn't it? That's probably what happened. Right, so where's the print code? Alright. So, basically, in 799 lines of code, we have a compute-based thing that renders where is it? GFX C. So it does a frame start, makes a command buffer, does a single dispatch, right? Not state of the art here. Like still work to do to get this right if we do multiple, but it clears the screen. And using a custom C shader, we're using a custom C compiler to compile this into Spivvy. So yeah, we can obviously make it more colorful. You can do something like this. Splat to SV dispatch index. Oh no, sorry. Gotta do some maths. Yeah, you want to like divide it by 800, right? So it goes from 0 to 1. Ta-da! Colors! There we go. So what does this mean? So this means we have a working Vulkan implementation on Linux, and we have an OS abstraction that we can now implement on Windows. So next stream, we'll get this running on Windows. And while we're there, like hopefully we should be able to get it set up. While we're there, what should we do? I'll think about it. We're either going to do some cleanup stuff and make the current Vulkan thing better, or we're going to think about the synchronization problem and write another shader. I think we might write another shader, and we'll draw a box that runs around on the screen, and that'll be our player to start off with. I think we're doing timestamp stuff in early. Curious about the performance of GPU pipelines. Also care about performance GPU. Okay. So I will be doing performance testing on the GPU side of things, and CPU actually. Because we are in our R&D session when we do our 3D R&D. Like I want to figure out like is this fast enough to do something with, right? So we are going to be putting in some perf stuff, that is for sure, at some point. I'm not sure about the VK semaphores on Windows. What do you mean? Because CPU interrupts on Windows, big stall. Yeah, I don't know about that, because they're the only primitive you have, right? Weird. Or do you mean actually waiting for it or something? I feel Vulkan boilerplate in my heart right now. Yeah, it's crazy. Like I have a love hate with the API. It's the stuff it enables you to do is awesome, but the way it goes about doing it is just like so bad. It works in the integrated GPU. No, I'm using AMD GPU. It will work with NVIDIA, and it'll work with like the latest Intel cards. Because I'm not sure if the latest Intel cards. Yeah, there's like we'll see. Right, so we're gonna go ahead and get this thing checked in. So this is VK. Right, so we've updated all of that. I think that's good enough. So there's an OS implementation that we can do. We need to get a build script on Windows. We need to figure out how do we do debugging, using Visual Studio. And also I might try and figure out while we're streaming, can we do WSL on Windows? So if people are following on Windows, could they compile it in the WSL for Linux? Sorry, Windows subsystem for Linux in Windows, and then run the Linux application, and does it work? So there's that thing to test out as well. Is that a good idea? Git commit -a. So we want to say like get Vulkan compute clearing the screen to a rainbow. There we go. Now I want to push that up, so I've got to do a dance here with this. I don't know why. I didn't have to do this with GitHub, but I have to do it with GitLab. Right. So for those of you who have access to the code, it's up on the GitLabs right about now. So you'll be able to download the latest and have a play. And Intel 512 600 maybe. Hopefully. Yeah, that's the thing. Supporting all this different hardware. There will probably be some issues in the future, especially as we have more capability. Hopefully not so bad though. Yeah, you can run X11 apps, isn't it? So I'm hoping it allows you to do Vulkan because it must do, right? There is. So I want to give that a go because then it means if there's something that's not implemented on Windows and people maybe struggle doing that, they can still compile it on the Linux side and get it to work. So that'd be good. That'd be good. Right. That was a really good stream. I'm glad we got graphics working in 2 streams from nothing. Very cool. Right. So let's drop some links, guys. So there's Discord if you guys fancy coming and hanging out. I post random stuff in there sometimes. Some videos that I'm watching. Sometimes there's like a conference that was on yesterday and today about rendering. I posted that one in there. I post about every day before I stream, 6 hours before I post about what we're streaming about. Yeah, and just a bunch of random programming chat as well. You can go in there and ask more long form questions if you have any about what we're working on or something like this, or anything to do with programming really. But yeah, I also have a Twitter where I'll be posting things as and when we start doing more graphicsy things. But yeah. I don't know what GPU specs are called in Vulkan, and they're called... Oh, GPU syncs. Right, sorry. Command Q, sync wait. In contrast, GPU interrupt. Right, I see. Yeah, I have no idea. I have no idea on that one. Oh, is this someone we can raid? No worries, thank you for coming, it's really cool. Is there any CPPs anywhere? Oh, here you go. This one ought to be good enough. Rightio. So the next stream is on Thursday at 6:30 p.m. GMT. It's the same time as the stream started, and we end. Well, we're meant to end like an hour before, but I really wanted to get this done, and we got it done. So, yeah. Right. Have a good Wednesday and Thursday. I'll see you on Thursday. Catch you all later. Thank you for coming.